Hello, everybody. My name is Cristina Palencia. As many of you, I am a science enthusiast, in particular in the fields of physical chemistry and nanoscience, disciplines in which I've worked several years after I obtained my PhD in 2010. I am currently working as assistant to the management board of the European EXFEL in Schönefeld, Germany, and as part of the steering committee of the International Year of Basic Sciences for Sustainable Development, I am co-organizing this 24-hour online event in which we share scientific content of many kinds for you. During the next 4 hours, I will drive you through very interesting talks, interviews, and also a panel discussion on gender equality. You can use the chat tool to place your questions or comments. And now at the beginning, I want to invite you to participate in the periodic table challenge that the IUPAC has prepared. Let me share a video with you.
Hello, everybody. You already know the periodic table of the elements, where all the chemical elements are grouped into columns and rows. But how well do you know these elements? I propose you to take the periodic table challenge, an online quiz that is produced by the International Union of Pure and Applied Chemistry, the IUPAC. Your challenge will be to answer 10 randomly chosen multiple choice questions about the elements. As any effort should bring a reward, you will first get a certificate from IUPAC if at least 60% of your answers are correct. But there will be more for this special edition at the occasion of the 24-hour online event organized by the International Year of Basic Sciences for Sustainable Development. Among the winners of today, we will randomly select 3 who will receive a poster of the periodic table signed by 13 chemistry Nobel laureates. You can play alone or with a team from 5 a.m. UTC 5 June to 5 a.m. UTC 6 June. So, how do we play? First, go to the homepage at iupac.org. You can just enter periodic table challenge in your favorite search engine. You will certainly find it easily. You can choose your favorite language, and then here, your difficulty level. Once done, you have to choose an element, which will be your avatar. Let's go. Now, be careful. You have to enter your name, and here in the school institution box, type IYBSSD so that you are sure to enter the special edition competition. Do not forget your email, your city, your country or region. Then send. Are you ready? Click on play. And here is the first question. And if you do not reach the 60%, you can just play again. But do not forget to follow also the very interesting talks, panels, discussions, interviews, videos we are proposing to you all along these 24 hours. We hope you are enjoying this event.
There is a small corrections that you have to keep in mind when participating to the periodic table challenge. Let me share with you this slide so we have it all clear. So you should put the abbreviation IYBSSD in the field city instead of on the field school institution. This will help to gather all the results that we will present at the end of this 4-hour time slot. And now it's time to start with the first of our speakers. She is Enrica Porcari. Her contribution has been pre-recorded because she was not able to join us live today, but let me introduce her. Enrica is currently the head of the IT department at CERN. She obtained a master's degree on social sciences by the University Milano and another one on international procurement management by the University of Rome Tor Vergata. She has over 25 years of managerial experience with telecommunications, technology, knowledge management, and communication activities related to development. She has been the Chief Information Officer and Director of Technology Division of the UN World Food Programme and has held several relevant positions at CGR, Science for Humanities Rated Challenges. Let's see her contribution.
Okay, good afternoon, everybody. I'm Enrica Porcari. I'm the head of the IT department here at CERN in Geneva. And I'm going to talk to you about advancing science collaboratively, how it generates technologies that are relevant for all. So let me introduce you to CERN. CERN is the biggest laboratory for particle physics in the world, and is based at the border between France and Switzerland, right next to Geneva. And our goal is to really understand the most fundamental particles and laws of the universe. We do that through 4 pillars. One is obviously research, which is one of the core elements of the work that we do. Collaboration, we collaborate with many organizations and countries worldwide, and I'll tell you about this later. Technology and innovations is the centerpiece of our work, pushing the boundaries of technology and innovation for everything that we do. And one of the pillars of our work is about extending the work that we do towards education and training at CERN and beyond. So we develop technology in 3 key areas for our work. One is the accelerator. The other one is the detectors, the development and the running of the detectors, and then computing, for which my department is responsible. So this is the Large Hadron Collider, the 27-kilometer tunnel underground, 100 meters underground, which contains superconducting magnets that steers particles around the rings, particles that travel at almost the speed of light. So what happens to these particles as they collide in 2 different beams, clockwise and counterclockwise, at 4 specific points, giant detectors record these collisions. So the 4 detectors are the home for large projects, CMS, ALICE, ATLAS, and LHCb, where this information is recorded. So what happens? These detectors are like large 3D cameras. I mean, when I mean large, the diameter of that detector is about 25 meters. So the detectors measure the energy and the direction and the charge of the new particles that are formed by the collision. The detectors take about 40 million pictures a second, but many of them are discarded because either we have seen them before or they're not useful at this moment. So only about 1,000 of them are recorded and stored. So stored where? They come stored in the CERN data center, where they're also further distributed through the WLCG, which is the Worldwide Large Hadron Collider Computing Grid, which includes over 170 data centers in 42 countries. To give you an idea of the size of the data that we collect and distribute, we have about 1,000 petabytes of CERN data currently available worldwide. So why is this important? So reaching these very ambitious scientific objectives requires that CERN focus and develops a lot of advanced instruments and new technologies to make CERN really a driver of innovation. But this is not only innovation for ourselves. We have a mandate, we are mandated by our constitution, but also we set up important programs within CERN to easily transfer our know-how to industry and society. So for example, we have set up 9 business incubation centers in member states, and we assist young entrepreneurs, small technology businesses in taking the technologies that CERN develops and our expertise to the market. So CERN also engages widely with international organizations and platforms to share the value of science and inform fact-based decision-making within empowered citizens groups. So CERN is an observer at the UN General Assembly and actively supports 7 of the 17 UN Sustainable Development Goals. So during my talk, I'll guide you through 6 of them. The number 5, the one on gender equality, I will leave it to my colleagues who will have a specific session on gender issues. So let's go through some of this Sustainable Development Goals. So number 3, good health and well-being. So CERN mission, as I said, is to extend science beyond what we do. So the technology that we have to develop for our own work, we always look for other implementations. So look at, and this is not new, as a slide says, it was 46 years ago that the PET scans was developed using CERN technologies. So, but many of the technology, we have a collaboration called Medipix that really looks at how technologies developed at CERN could be used in the medical sector, both in therapy for cancer treatment, in imaging and diagnosis, for scanning techniques that are more and more refined, and for developing biomedical technologies and medical and biomedical research. A couple of examples, we develop particle accelerators that are used in hadron therapy for the treatment of tumors, already operational here in Switzerland. Develop medical imaging using scintillating crystals for PET scanners. And then we have pixel detectors, what you see here is in Medipix, for X-rays, and those were used in some astronauts' missions. So next one, I want to talk to you about CARA. So when the COVID pandemic was in full swing, CERN developed COVID airborne risk assessment, a system to understand the transmission of respiratory pathogens, in particular for the COVID virus. And we developed it for ourselves because we wanted to make sure that our staff would feel comfortable when there was the re-entry, when they needed to participate in meetings, but also because in some of the work that is done here at CERN cannot be done remotely. They need to have engineers, technicians on the ground. So how did we do it? We developed these systems. Now, the World Health Organizations became very interested in it, and together with us is extending the model to what is called now Chimera, which is the CERN airborne model for indoors risk assessment, which looks beyond COVID. So we just use the physical model, the same engine that we had with CARA, looking at using different parameters for other circumstances. So one of the examples of technology developed here that then is used for other uses. SDG 4, quality and education. So education, as I said earlier, is really at the core of our mission. And the inspiring rising generation of new scientists is one of our core mandates. Just to give you a few numbers, we have about 70,000 school children that visit CERN every year, 10,000 teachers that have been trained by CERN since 2006, thousands of school students that perform hands-on experiments here at the CERN campus on what is called the CERN School Lab. And then every year we register thousands of PhD students to do their research and further their education. So education is of particular importance to us. So much so that we take as our education efforts outside of CERN. Here is what I wanted to show you, the CERN School of Computing, which is what my department does. It's a school that was launched in 1970, which this year reaches its 44th edition. And since then, he has trained over 3,000 students of 80 different nationalities in 22 countries. So it's a school that travels the world and brings education closer to the people. CERN doesn't only have a school of computing, it has a school of physics, school of accelerator, but I wanted to focus on this because I am definitely more familiar with it. So number 7, affordable and clean energy. What does CERN do to improve the energy cleanliness in our world? So just a couple of examples. We're developing high power transmission that lower the losses of electricity transmissions, and therefore it could become an enabling technology for overall a more sustainable transmission of electric energy. So imagine, again, this is work that we will have to do at CERN for our own work, to run the accelerator, to run the cryogenics, to run the magnets, to run all the infrastructure that is down in the tunnel that I showed you earlier. This technology, which continues to be improved and innovated, we look at it at applications for others. In fact, we just entered a partnership with Airbus on future clean aviation to see how the superconducting technologies that we're using for our accelerator could be used for to ideate future low emission airplanes. CERN also started an innovation program on environmental applications in March 2002 to really harness all these innovations potentials in environmental technology. We run a fund, a competitive fund, to look for further ideas to co-develop with us innovative solutions. So SDG 9 on industry, innovation, and infrastructure. So look at the picture on the top left. That's Machina. That's a device that CERN and INFN, the Italian Institute of Nuclear Physics, have developed, and it is a compact, transportable accelerator for the non-destructive analysis of historical artifacts and artwork. So it's now included it's in Florence, I think, and it's doing its work there to analyze the masterpieces and that are held in the museums in Florence. Now, Insight Artist, the next one I wanted to talk to you about, is a Czech startup that is built on a CERN time-pix detector that is basically is an advanced X-ray source that helps determine the genesis of some of the artifacts. I think most notably, as in this picture shows, is the device that was used to identify that the Madonna and the Child was actually created by Raphael himself. So one last thing, maybe the car, together with the Zenseact, a startup in Sweden, we looked at opportunities to increase for autonomous cars to make faster decisions, and hopefully bring in safer autonomous cars to the streets soon. SDG 16 looks at peace, justice, and strong institution. I think as CERN itself, that as an organization that is celebrating its 70 years next year, is an organization that historically brings nations together, building peace through science. We have over 110 nationalities that work together at CERN, irrespective of their religions and government systems. And some of the countries that work with CERN are opponents at the political stage, but at CERN find an honest, a neutral place to be able to just do science. And it's important also to know that according to our convention, all of the work that we do here at CERN has to be put in the open and free access to everybody. Open science is again, as I said at the beginning, is the center of what we do. Also in the open science, open data, CERN developed an open science policy recently, and everything that we do, from tools to hardware to data, is supported by this vision of making our work open. So in the IT department, we develop tools that are open and used to by other organizations. Just an example, Indico, which is a conference and meetings and events scheduler and organizer, with the data, with the document repository linking to video conferencing, is used every day by over 10,000 users, and manages since its birth 700,000 events. So it's a very successful application of some of the work, again, that we did here at CERN, and then we extend to others. As an example, I found this slides from 2019, how many users within the United Nations use this technology. Again, in support of open science and open research, CERN developed Zenodo with an engine underneath called Invenio RDM, which is an open source technology that allows for open document repositories with perennial DOIs, so they can be papers can be found all the time by everybody. Continuing on the partnership, as I said, CERN in its 70 years has been a model for open and inclusive collaborations. 23 member states, 10 associate member states, observers, 50 cooperation agreements, many staff from different parts of the world. Let's just look at the size of the 70% of the physics research in the world is done here at CERN. And CERN extends its arm by cooperating with many UN organizations to, again, amplify our impact on society of the work that we do. As an example, we host here at CERN since 2001 UNOSAT, part of UNITAR, the United Nations Institute for Training and Research. As UNOSAT is an organization that looks at ways to develop mapping, credible and reliable and timely mapping for flood detection, shelters for refugees, and they're used by United Nations and other humanitarian organizations alike. So we use them. We not only host them here in terms of basing it on the infrastructure of CERN, but we develop with them a lot of AI, artificial intelligence, for satellite imagery analysis. It was only last week that I was in Lebanon, inaugurating the High Performance Computing for Lebanon, a project that we launched a number of years ago to reuse some of the technology, some of the equipment that is used here at CERN, and then after it finishes the timeline, a life cycle here, but it's still very usable hardware. What we do, instead of throwing it away, we refurbish it, we clean it up, and we donate it to universities or organizations that request it. Last was, as I said, is a partnership of universities in Lebanon and in partnership with public sector organizations in Lebanon, and we were able to inaugurate the data center there at the presence of the Prime Minister and various ministers. Really, I was personally there, and I could see that how this platform would really promote innovation, research, and scientific discovery in the country. There was a lot of enthusiasm from young people who attend universities and now have facilities to be able to do their work better. So I hope that this short speech was able to give you a few glimpses of how at CERN we strongly believe, not only we believe in theory, but we practice science collaboratively, and we work hard to indeed generate technologies that are relevant for all. Thank you.
I want to thank Enrica for the effort to record her contribution for this event today. And now we can go on with our next speaker. He is William Garnier. He is Director of Communications, Outreach and Education at the SCA Observatory. In his position, William is in charge of developing and delivering the global communications strategy for the observatory. William has been working in science and astronomy communication for about 20 years, working for multinational organizations, including the European Southern Observatory and the ALMA Observatory in Chile, and over the last 10 years, the SCA Observatory, an intergovernmental organization headquartered in the UK, poised to deliver the world's most powerful radio telescopes in Australia and South Africa. William is passionate about big science, for the science discoveries these large-scale research infrastructures are delivering, but also for all the ecosystem around this and the wide range of ramifications they have that permeate society. This is what William will tell us about today with a talk entitled Beyond World-Class Science, Building a Sustainable Radio Astronomy Observatory. Hi, William. Thanks for being with us today.
Hello, Christina. Hello, everyone. And thank you very much for the invitation. It's a great pleasure today to be with you. I must say I'm on childcare duty as well. So if you hear some children in the distance, don't worry about it. So yeah, thank you. And thanks to my son colleague as well, who introduced the topic very, very brilliantly. So today I will be talking about the SKA Observatory, SKAO, which is a multinational radio astronomy facility. So, poised to deliver world-class science. But today I will not focus on the science. I will explain how we are really endeavoring to build a sustainable radio astronomy observatory. So maybe starting with to set the scene with the SKAO's mission. As you can see in there, our mission is to build and operate cutting-edge radio telescopes to transform our understanding of the universe and to benefit society through a global collaboration and innovation. So that second part is really, really relevant, obviously, for the topic of today. And that's what I will be talking about. But as you can see, it's right there in our core mission for the observatory. So I will just set the scene very briefly about 21st century astronomy. So sorry for those of you not familiar with the electromagnetic spectrum that you can see here. It's basically the light which is emitted by objects in the universe. And what we can see with our own eyes is just the visible part here in the middle. And you can use bigger telescopes, optical telescopes, to have access to even more information about that part of the spectrum. Or you can use some other facilities on the ground or in space to observe different phenomena in space. And if you go to the left-hand side here on the radio regime, you can see the radio regime, and you can see all these facilities. So many of them are sort of part of the SKA endeavor, and I will talk about it in a minute. We call them the SKA precursors and pathfinders. And you can see just around the corner, or just we can see it on the horizon, the SKA telescopes, which are about to be built in Australia and South Africa. But as I said earlier, we are an international observatory, the SKAO, and we actually have a unique footprint around the world. As you can see with the dark blue here represent all of our partnership, many countries being members of the observatory and others being observers in the process of joining as a member. So we've got 16 countries, and we really bridge the gap, north, south, and east, west as well, bringing together countries from the 5 continents. And an interesting fact as well is that 11 of these countries are part of the G20, 6 are part of the G7, and 3 are part of the BRICS, which is, for those of you not familiar with the concepts, which represent Brazil, Russia, India, China, and South Africa. So the last 3 are part of the SKAO partnership. So it's really a unique endeavor, which has a number of ramifications in terms of the impact as well, as we'll be talking about in this talk. So who are we? We are an intergovernmental organization, just like CERN that you heard about just now, like ESA, ITER, ESO, and others. And we are one global observatory building 2 telescopes on 3 sites. So the headquarters is in the UK, the George Bank site that you can see here on the left-hand side in the shade of the majestuous Lovell telescope, which is quite fitting scenery for us, obviously. And then we are building these 2 telescopes, one in South Africa and one in Australia. And the sites have been chosen because we want to be as far away as possible from us, from ourselves, from humans, from civilization. because we don't want interference generated by humans. And the total project cost is over 2 billion euros. So that's for the construction of the telescope and for the first 10 years of operation. I said I will not be talking about science, so I just have this one slide here, which is quite daunting. It represents, roughly the breadth of science cases that the SK telescopes will be able to address. So it goes from the, looking at the first stars, the formation of the first stars and galaxies after the Big Bang, to the pulsars, the study of the pulsars and the gravitational waves to try to challenge Einstein's theory of relativity. And we'll also be looking at, trying to understand what dark energy is, what dark matter is, and also, if there is life out there, to try to detect it. So as you can see, it's really, really wide, and it covers the entire spectrum of astrophysics and cosmology. Right, but today I'll be talking about, the socioeconomic impact of the SKAO. And so just to give a definition here, it's basically the non-science impact is basically the contribution that research makes to economy, society, culture, and sustainability. There are many definitions out there. That's the one we are using. And I will be giving a couple of examples for each of these categories in a few minutes. Just to give a bit more context as well, in the last few years, the impact seen has evolved dramatically, and the non-science impact is now a clear driver for investment. So it's not only a byproduct of investment in larger scale research infrastructures, it has really become part of your business case, the driver for investment. And it is certainly true in the case of the SKA. And as early as in 2010, so over like 10 years ago, 13 years ago, this was thoroughly discussed by our partners as well, to make sure that the impact beyond science would be really defined. And as I said earlier, we are an intergovernmental organization. This means we are governed by a convention, a treaty, which is this high-level document which has been signed by countries, by ministers in our countries. And so you can see it here. Actually, I've got a photo of the first page of the convention, which is a very prestigious document. And this is the preamble. What you can see here is the preamble of the convention, which basically gives like a number of high-level principles, high-level statements from countries. And what's interesting for us is that one of them, as you can see, I will highlight it here, one of them is exactly about what we are talking about here: embracing the potential for scientific discovery to contribute to advances in technology and innovation, and to deliver a broader benefit for industry and society. So it's right there, it's right in our convention. So that means that our members, they are expecting us to deliver on that commitment, which is exactly what we are planning to do. And so what we do, we usually relate, and my colleague from CERN did the same as well. We relate to the global challenges, because this is something that people know, in particular the policy and decision makers. It's something that resonates with them. And so we usually link our activity, non-science activities, to the SDGs. And so here you can see them all on this slide. And actually, what I've done here is really highlighting those SDGs that we are directly contributing to as a radio astronomy observatory. So some of them, can seem pretty obvious, like quality education, decent work and economic growth, or industry innovation infrastructure. Others, not so much. They are not necessarily linked to activities like the ones that we are undertaking, like radio astronomy. But in effect, we are addressing all of these SDGs that you are seeing here on the screen. In a humble way, let's be humble here. We are only one observatory, but we are trying to do our best to really play our part in addressing these global challenges. But when we talk about impact in the SKO partnership, we need to give a bit more explanation. We, as an intergovernmental organization, we are pretty young. We were born only 2 years ago, so it's really early days for us, to start engaging on that impact journey. It's only just starting. But the SK project itself, it's been in the making for over 3 decades. So the impact of the SK project goes much beyond just the observatory, and it involves a number of countries. I showed you the map a bit earlier about all these countries involved. And it is fair to say that across all of these countries, in particular the host countries, the telescope host countries like Australia and South Africa, there's been a lot of investment and a lot of work being done the last few years in terms of developing R&D, in terms of building skills, in terms of developing science, engineering, and industrial capacity as well. So all of this is already generating impact locally, nationally, and globally. And so what we are planning to do as an observatory is really to build on this and to expand this impact even further. So now I will focus, again, I will give a few examples on these 4 pillars of impact, starting with the economy, bearing in mind that I could take an entire week almost, to talk about a number of impact stories and case studies across the partnership. So I just highlight a few here just to give you a taster of what we are talking about. So this one here is coming from China, and it's talking about some summer schools which have been taking place in China. And actually, this is the case in many other countries as well, of the part of the SKO. And it's really about equipping university students with the skills in data processing, in imaging capabilities. And the schools, they've been training hundreds of students over the last few years from all over the country. And some of these have already become successful researchers in their own country and taking part in growing the radio astronomy field in China. So this has already a very important impact. And then I've got another one here, which is about the SK dishes, which we are building as we speak. So it's another collaboration, global collaboration in action. And here you can see the flurry of activities which are taking place now across many countries. So the main dishes, the main reflector and the pedestal of the dishes are built in China, manufactured in China, but other parts are built in Sweden, in Spain, in Italy, in South Africa. So that's really, in all of these places, there's a lot of innovation going on, and there's a lot of highly skilled jobs which have been created just for that, for the production of these dishes. Another great example coming from South Africa. So these are some data from South Africa. An impact assessment has just been done, actually. So it reflects all the investment that has taken place over the last 12 years in South Africa, which covers a range of human capital development programs in South Africa, but more generally across Africa as well. And as you can see, it has enabled hundreds of individuals to benefit from training, from bursaries. 1,400 grants have been awarded since 2005. 250K euros were spent only last year on training. So that's quite impressive. It's big numbers which are already having an impact in South Africa, but as I said, across several African countries as well. And we as SKO, as the SK Observatory, we are determined to follow that trend as well. And we are working very closely with our partners from the South African Radio Astronomy Observatory. And we want to play our part in the local economy and the national economy of our countries, developing skills, supporting the social development opportunities, and promoting the local heritage as well. I won't go into the details, but obviously you can go back to these slides afterwards. This is a snapshot of the total amount which has been invested in South Africa through all of these programs already. Societal impact, another important one as well. So this one is a great one as well. That's like an astronomy festival. There are many around the planet, obviously. This one is an example from Australia, the Astrofest festival, which has been taking place for many years now. And it's already attracted tens of thousands of visitors, young people, family, and so on. And really a great way to enthuse the next generation, to inspire people about the wonders of the universe, and more generally, the relevance of science and basic sciences for humanity. And it's a great way of inspiring kids and to get kids into STEM disciplines as well going forward. This one here is another very, very fantastic example as well, which is only for from a couple of years ago. It's a great impact story from South Africa. It's a formidable example of skills transfer from radio astronomy to other parts of society, in this case, the medical sector. So during the COVID pandemic, the government entrusted our partners from the South African Radio Astronomy Observatory to design and to build respiratory ventilators. There was a big shortage of ventilators in South Africa and very expensive ventilators. And our colleagues, thanks to the expertise that they had gained in building a telescope in South Africa, they were mandated by the government to design low-cost ventilators, which they did successfully in a matter of months. And then these ventilators, were manufactured and spread across the country in all the hospitals in need. And that was revolutionary and really, life-saving, literally life-saving. So, isn't it a fantastic example of how basic science can have a direct and immediate, impact and ramifications in society? This one as well has been touched upon by my colleague, science diplomacy. Just like CERN, the SKO is another great example of science diplomacy tool, which allows to foster international connections, encourage these high-level connections, and really act as a vehicle for collaboration, for peace, and for development as well. So that's something which is another element very important in our partnership. The culture impact on the culture. This is another great example coming from Australia. So here we are talking about an agreement, which we call the Indigenous Land Use Agreement, which has been signed now after many years of negotiation, being signed between the Wurundjeri Yamaji, who are the traditional owners and native title holders of the site where our telescope will be built in Australia, and the Australian government. So that's an agreement which is absolutely essential for us, which is, if you like, a social license to operate. It establishes working practices in terms of the preservation and promotion of the cultural heritage of these places. It really establishes a true partnership between us, the SK Observatory, and the Wurundjeri Yamaji, the traditional owners of the site. And it's also a way of ensuring that we provide job opportunities for the Aboriginal populations around the telescope site. And so there's a number of education opportunities, scholarship, apprenticeship, which are part of this agreement, which we will be delivering, and which will be valid for the next 50 years of operation of the telescope. And as part of the signature ceremony, we had the privilege to be granted a name by the Wurundjeri Yamaji for the site of the telescope, which is Inyarimanya Ilgari Bundara, which means sharing the sky and stars, which is a fantastic name that they gifted to the site. Another example of cultural impact of a project like the SK Observatory, it's really about being embedded in the art and pop culture. So, for example, recently, the last few years, we developed an art exhibition, Indigenous Art Astronomy exhibition, bringing together artists from across the two sites of the telescopes. And this exhibition has been touring around the world. And it's a great way of reaching out to the art enthusiasts and maybe the hard to reach audiences, not really interested in science, but interested in art, and to tell them about the beauty of the universe and how relevant that is as well. So that's a great exhibition that we have, which we're really proud of. And we also have occasionally appearances in the pop culture, in TV series, cartoons, and books. And so here I've got one which is from a few years ago. Some of you will recognize The Big Bang Theory, great TV show. And if you look closely in the back here, you can see some of the SK posters that we developed for the occasion. So again, a great way of being there, in the pop culture and being embedded in society. And I will finish by a couple of examples on the sustainability side of things, something very important for us. So renewable power. Here you can see a photo of an off-grid solar hybrid power station, which is already used in Australia to power the site, so to power one of the telescopes. And now that we are building our own telescope, we are planning to expand on this PV station and to really make sure that we are using, we've got a high level of penetration of renewable. So that's great. This one that you can see here, it's a 1.85 megawatt solar array, so quite impressive. And then an interesting fact there is that 800,000 liters of diesel and 2,000 tons of CO2 per year have been avoided just because of that, because of the installation of that station. And again, bear in mind that we will be building one even bigger than that. So the impact on, or the non-impact on environment, let's say, will be obviously very, very relevant. And just to say that for us, an additional challenge is that we need these stations to be radio quiet as well. So that comes with a number of complexity, which we are addressing as well. And then just to finish on this slide, just to list some other initiatives. As I said, I mean, there's so many that I couldn't list them all, but initiatives around the sustainability. So in South Africa, the area around the site of the telescope has been declared a national park, which added over 3% to the already existing surface of all the national parks in South Africa. So that's quite impressive. And obviously that allows to extend the preservation and the protection of species, the removal of invasive species, and it's very important for research as well in terms of monitoring and so on. And in Australia, as I said, very important for us to respect the communities around the telescope site. There's been a number of what we call heritage wall covers, which have taken place the last few years. 600 hectares of land have been covered to ensure the full protection of the sacred sites and the cultural areas of relevance for the Aboriginal community, the Wajari Yamaji, just to make sure that we don't disturb these sites which are sacred for the local populations, and we stay clear of that. So we had to move some of the stations for the telescope elsewhere, just because we want to protect these sites. And this work has been led by the Wajari elders in collaboration with our partners in Australia and some archaeologists and anthropologists as well. And our role now is really to document and to protect this heritage on site. Again, I'm sorry, I really had to cruise through a few of these examples today. Obviously, you can have much more information on our website. We can see here on the left-hand side, dedicated section of the website where you can have other examples of how we are benefiting society. And you can also find a foundational document, which is the construction proposal. And in there, we've got like an extensive paragraph about the impact as well, if you want more information about us. So I thank you very much. And obviously, feel free to get in touch if you want more information about what we do. Thank you very much.
Thank you, William. So since we have a couple of minutes left, I will take the chance to ask you a couple of questions, if this is fine. So you were talking about the socioeconomic impact. Do you have some figures? How diverse is SCA, the staff, in terms of gender, age, nationalities?
Yeah, so we've got, I don't have the numbers in front of me, but we've got over 25 nationalities at the headquarters in the UK. And now we are building the teams in South Africa and Australia as well. And so what we want to ensure we've got diverse teams of people. So we are recruiting internationally. And in terms of the gender balance, again, I don't have it in front of me. It depends depending on the functions in science, engineering, business enabling. There's some more work to be done. Obviously, we are a reflection of the entire field. For example, in engineering fields, unfortunately, there are much more men than women. We are a reflection of that, but I think we are doing pretty well. We are, above the curve. But again, more work is being done. So we are participating in a number of initiatives to really try to appeal, to a wider audience and make sure that we are attractive to female applicants for this sort of job and so on. And we've got some role models in the organization as well. We are doing some public engagement talks, just to say, there we are open, to anyone, wherever you come from, whatever your ethnical background is, or whatever. We want to welcome. We are inclusive. We want to welcome everyone.
Thank you. And I was actually very surprised about the construction or development of respirators during the pandemic. Do you know if SKY is also involved in any other kind of medicine development, or that was an isolated event due to the pandemic? And I also wonder where the authorities approaching you, I guess.
Yeah. So during the pandemic, I guess, like everybody else, especially at the start of the pandemic, we were wondering, what can we do? How can we help? And I know that I didn't list that here, but across the partnership, many of my colleagues, even in communications and in some other fields as well, found some use, using their own skills to help tackling the pandemic. In India, for example, colleagues developed, there was a lot of fake news, well, just like everywhere else. But I've got this example in mind, which has been told by Indian colleagues, a lot of fake news. So they use their communication skills to tackle that and to develop some fact sheets and material, to really convey the actual information about what we knew at the time, about the disease, just to try to tackle all these fake news. And so redirecting their skills and their experience into that field. Other examples in several other countries as well. The development of some apps in Australia. Some astronomers developed some apps, to track the COVID-19, across the society. That was used, to great effect. But no, I mean, apart from that one-off, the skills transfer to design and develop these ventilators, not really. This was really a one-off. Again, we are talking about colleagues who, starting from scratch in South Africa in the early 2000s, in a matter of 15 years, have built capacity, have developed the skills, and so on. And they've built what is now the world's most powerful radio telescope. Okay, so they acquired they did a lot of mistakes. Obviously, they learned a lot of lessons, and in all this process, developing their engineering skills, systems engineering, and project management skills, they demonstrated that they could do it. They could make sense of a complex system and build the world's most powerful radio telescope. So the government say to them, okay, now we've got some other challenges, namely the lack of ventilators. We want you to use those skills and to transfer those skills onto that. It took just a matter of months, literally, for them to discuss with the experts, medical experts, to understand the needs of the patients and so on. This, look at what was existing in terms of the ventilators and try to break it down and to develop low-cost ventilators, which they did. And that's just a fantastic story in itself.
Definitely, thank you. So it's a pity that we don't have much time to keep listening to all the interesting examples that you are showing us. But I thank you for your contribution. And now we are going to start with the next section. So we are going to do some interviews with scientists. And at the beginning, we have 4 recorded interviews with Mónica Turcato, Ana García Tavares, Camila Safreitas, and Sarmista Paul Duta. Let me share the video with you.
Hi, my name is Ana García Tavares. I'm from Spain. I'm a physicist, and I'm working here at European X12 as a software developer. I was doing my PhD at CERN before in Geneva, and then I moved to Germany. So basic science drives knowledge, and this helps functioning societies and democracies. Also brings countries the opportunity to be competitive in the global economy. Basic science aims to understand the universe by observing and analyzing physical, chemistry, and biology processes that happen in nature. Also here at European X12, science that is being carried out is framed in a way that this also answers societal challenges. This could be health problems, climate and energetic problems that our society is currently facing. Also, it's important to remark that these basic sciences normally imply drive the existing technology to the limits. So in order to perform certain experiment, we need to improve the existing technology, and this has an enormous impact in the society because it leads to to better technologies, not only to better technology, but it also drives companies and industry to the next step in being more competitive in the global economy. How we can see this at European Excel? We can see this in the superconducting magnets that are used in the accelerator, because this superconductivity, the things that industry learn, can be then later applied for transporting energy, or in the case of the instrument, they use detector to detect the X-rays and can be later used in the medical applications. So I think one very important breakthrough would be getting more efficient renewable energy. So we know that now the renewable energies are it's a very hot topic, and people really want to get, countries want to get almost all the energy based on these resources. One of these examples is the green hydrogen. So green hydrogen refers to method to obtain the hydrogen in a clearer way. So hydrogen is now has been investigated for the past years, and many industries want to use it as a source of energy. But the main limitation is the way that is obtained. So green hydrogen is obtained by splitting water into these components, hydrogen and oxygen. But this process requires a lot of energy. So scientists at DESI, by using the accelerator, the synchrotron petasy, and trying to understand how this process can be performed with less energy. So these studies could be potentially continued here at XFL, where we have a bright X-ray, and where we can study this chemical reaction that happen in a short time with a more resolution.
Hello everyone, my name is Camila. I am a Brazilian astronomer, and I am currently finishing my PhD at the European Southern Observatory in Munich. And today I'm going to talk a little bit about basic science and diversity. So as an astronomer, I hear a lot about why do we need basic science as a society, and I just want to bring up one example that I think it's very good to illustrate this. So in 1800, Herschel, who was an astronomer, was studying the colors of the sun. More specifically, he wanted to understand different temperatures for different colors in the sun. To do this, he used different filters, and basically he created a rainbow, and he analyzed the temperature in each color of this rainbow, right? What was interesting is that he realized that where you had no colors, where you shouldn't have any change in temperature, you actually still had some increase in temperature. And basically, this is how we discovered that the light is more what we can see. This is how he discovered infrared. So he was not looking for applicable reasons to use infrared, but this is how we, for the first time, realized that the light is much, much more of what we can see. And then today, we use infrared broadly as a society, 200 years later. So basically, we need basic science to build knowledge, to discover things, not necessarily to apply it technologically or not, but we need this basic science to discover new things, and then maybe in the future we can apply those things for new technologies, new solutions for medical problems, or even solutions, for example, for global warming. So this is why we need basic science, to build knowledge that, well, in the future we can use in different ways. Another good example is that when we were studying electromagnetism, no one was necessarily trying to improve candles or how to live in the dark. And then today we have electricity, internet, and all of this, and this phone that allows me to record what I'm saying to send it to you. So this is one thing why we need basic science. Another thing is why we need diversity in basic science. So basically, I mean, not only basic science, everywhere. But basically, diversity can make science and everything else more efficient when you bring different people to the table, when you bring different people with different views, with different experiences, looking at the same problem. You will try to solve this problem in many different ways, and then you will find the best way of doing it. If you imagine a room with 10 Albert Einsteins, of course he was a genius, but all 10 of them will find the same solution for the same problem. But if you put a room with 10 different people, we might find different ways of solving things, and we might find some things that are more efficient than others. So this is why we need diversity, not only in basic science, as I said, but anywhere in life. And how can we increase diversity? Well, I believe some policies are necessary because, especially in science, especially in the STEAM areas, it's very dominated, very Eurocentric, and dominated mostly by men, and especially white European men. So we do need policies to bring people together, to bring people from different places. Like me, I come from South America, and you put all these people together and you do a better science, basically. But yes, to do this, you need policies, public policies, to start making this change, because it will not happen naturally. People will not simply come from their countries, from their background, to a place that they don't feel welcome or they are not heard. So you do need places that welcome these people, that bring them together and make it possible for them to thrive. So this is my view on basic science and diversity. I appreciate very much this invitation.
Hello, I'm Monica Torcato. I'm the head of the detector group at the European X-Well in Schönefeld in Germany. The detector group takes care of the detectors of the European X-Well, which are basically large cameras. Their scope is to record the X-rays. The X-rays come from the machine, hit the sample that we want to study, and we basically record the images out of them with our detectors. So I think they have to think ahead, right? Normally policymakers, right, they are elected and their mandate is 4 or 5 years. And if you invest in science, you cannot expect to have an immediate return after 4 or 5 years. It's the return time is much longer. But what happens is that if you invest in science, science gives you all that makes your future better, right? If you think about fundamental science, of course, you're farther away from what impacts on your normal life, right? But if you look to science which is more applied, like for example what we do at the European X-Well, where we study to find out the structure of viruses, where we study materials to have, for example, better batteries in the future, or better memories for your hard disk, for your computer. This is something, if you do an experiment today, you cannot expect an outcome tomorrow, not even at the duration of the mandate of a politician, right? But you have to invest now to have the outcome and what makes your life better in 10 years from now. And especially now that we live in a context where we see climate changes, right, and environmental problems, and sustainability is becoming very important. Finding a more efficient way also to use our energy is vital, and on that it's only science which can help. Yeah, that's a really difficult question, because I really like the scientific community, because I think something like races is, I wouldn't say non-existing, but really low, because what we care is that we can work with a person and the person works well with us. This is independent on gender, on race, on color, on sexual orientation, anything, right? This is what we normally care, and this is what I experience in my daily life. If we think about minorities and the diverse environment, so I have the fortune to work at the European X-Well, where I meet people of basically a lot of countries, right? If we go more specific, and in my case, right, I'm a woman, and still in sciences like physics, the women are quite underrepresented. This cannot be solved by, let's say, hiring more female scientists or physicists at the European X-Well, because they are already much less than men out of the university, right? So if in physics there are 15% of women, you cannot expect that then in a research institute you have 50%, right? This doesn't work. I think what really helps in this respect is stimulating and encouraging girls to go in this direction because they have the capability. Yeah, it's not that they are worse than men in this respect. And also seeing, I think, example of women who can do this work well. And I think we have many around, right? And girls shouldn't be discouraged by the fact that it's a tough job, that it's difficult to have a family if you have this kind of a job, right? There are a lot of ladies who are good medicine doctors, and this is also a very challenging job, and I don't think it's less difficult than being a physicist. It's just that women culturally think they are more used and good to in works that imply taking care of people. But I think also science, women and science make a very good match because they bring a lot of, they bring a different perspective, and they bring their common sense, they bring their capabilities also there. So I think encouraging girls since a young age and giving them good example could be really a good way to increase the number of women in science like physics, for example.
Hello everyone, I am Shormishta Baldatto, a PhD student at European XFEL, Schönefeld, Germany. I am currently working with FXE Instrument Group, and I am investigating the metallophilic interactions in dimetal complexes, where I need to find out the origin of these metallophilic interactions and their electronic and structural changes in their higher excited states. Basic science is very important for our society for several reasons. Firstly, it drives the technological achievements and also the innovations in our society. For example, if you talk about the smartphones, internets, televisions, and various medical instruments, which are really rooted in basic science, and it's the results of the innovations and which involve the basic science. Secondly, it expands our understanding in the natural world and often leading to the unexpected discoveries which have very important impact in our societies. Additionally, basic science is the base for various other applied sciences, and it shows us how we can make a very well-being societies and the path for the innovations. Policymakers play a vital role in advancing science and research. They can allocate various resources, establish research funding framework, and also create a fruitful environment for the researchers to show their research and to improve their innovations. And if we talk about more about the funding, policymakers can make some surety for this kind of funding for looking in depth for a part, and also that funding should be stable, predictable, and accessible to the researchers who actually need the funding. And this funding should be they can use for their research purpose. Policymakers should also prioritize science educations, collaborations between the industry and academia, and also promote their researches to the whole world, so the researchers can be more motivated in their research. To build a more diverse scientific research community, we must address the systematic barrier that hinder the equitable participations. For educational institutes and research organizations should actively work towards increasing the diversity and their recruitment process and how they find out the new joinees in a diverse situations, and also outreaching the efforts that should target diverse communities to inspire interest in science from a very early age. It's very important. like we can involve science educations initiatives in schools, community engagement programs, and also like some kind of mentorship opportunities, along with promoting equal access to education, science, innovations, and support the represented groups around the world. And additionally, like addressing systemic biasness and stereotypes within the scientific community is very crucial. That also need to be removed immediately from the society to make a better happening in the world. Looking ahead to the several scientific breakthroughs, it would be a transformative impact on society. Firstly, advancement in renewable energy and technologies and energy storage could like be a very good transition stage for us in this world. And it's not only this energy storage, but the breakthroughs in solar power, wind energy, energy efficient materials, and grid scale energy storage solutions. This could revolutionize our world. And secondly, the advancement in healthcare, such as like the personalized medicine and gene editing technologies, which can be a huge breakthrough for this society. And most importantly, the breakthrough in artificial intelligence and machine learning could revolutionize various industries, including transportation, finance, and healthcare, enabling more efficient and intelligent systems. These all scientific breakthroughs hold the potential to address global challenges and improve the quality of life of people all around the world. Thank you.
Thank you. So now we are going on with some interviews, and I would like to invite Ramon Bernardo Gavito. Hi, Ramon. So he is an assistant research professor at IMDEA Nanociencia. Can you tell us something else about your research?
Hi, Cristina. Thank you for having us. Yes, well, I'm a physicist here at IMDEA Nanociencia. I study mostly two-dimensional materials and different ways they interact with light and electrical fields to make mechanical oscillations.
So would you say that your work is mostly basic science, or it's more applied science?
Well, I would say somewhere in between. The phenomena we study are really interesting in terms of basic science. We study nonlinear oscillations in these kind of materials, and which are very thin, and they can lead to chaos and lots of different interesting phenomena. But they also can be used as mass or gas sensors or as actuators. So they do have an application at the end.
So I think it's very clear for everyone why applied science is necessary, but what do you think about basic science? So why do we all need that research keeps on basic science?
Well, basic science is the foundation of all the applied sciences, and then of technology, of course. So if you think of the most hyped technologies at the moment, like quantum computing or artificial intelligence, they both depend ultimately on basic sciences, right? Quantum computing depends on the study of quantum physics. At the end, the hydrogen atom is back there. And artificial intelligence rests on the most basic of science, which is mathematics. And then if you listen to the previous speakers, then no matter if you look at big celestial objects or the very small subatomic particles, you are having an impact in society, in culture, and then, of course, technology.
And so you saw we were already asking about the breakthrough. So try to be a little bit imaginative. What do you think you would like to see coming in the next years as the most important scientific breakthrough?
Well, that's difficult to say because there are lots of fields, but I think most of us will always think on the energy and the availability of resources. So we'll know we keep growing and growing as a society exponentially, just in the numbers. and each individual keeps consuming more and more energy and more materials. So we need to find a way to keep this world going. So we need to be able to produce energy from renewable sources, and most importantly, to reduce the energy and material consumption. So we have to look at a way, and that goes through basic science and both through behavior as a society to reduce our impact in the environment. Yeah.
Okay, thank you very much. So I'm going to invite now Raffaello to continue with the interviews. Thank you, Ramon. Welcome, Raffaello. He's a junior assistant professor at the University of Bologna. Can you also tell us, in your own words, a little bit more about your research, please?
Sure, thank you very much. I'm a fixed-term researcher at the University of Bologna, and my field is basically focused at the investigation of materials and devices for the conversion of sunlight into renewable chemical sources. So they can be either energy media or they can be chemical commodities. So I think I'm quite well fit to this event, since basically everything I'm studying is related to sustainability. So it's related to the idea of converting a wide and abundant energy source such as sunlight, and use it in order to store it into chemical compounds such as hydrogen, for instance, from water, from simple water, or in some economically important compounds such as biomasses derivatives that have an economical impact, so that I can couple both the environmental sustainability and the economical sustainability in a single application. So that is very basically my field of study and what I'd like to do in my life, basically.
So then it's more or less in the middle between basic science and applied science, right?
Surely, it's probably mostly applied science, but without basic science, we can't do nothing. So that's the.
So if we are talking about research actually need funds, etc. So when asking or proposing to get some funds, how important is to balance basic science and applied science when a researcher wants to get support for the research?
Yeah, I think today it's really a challenge, because most of the policymakers are aiming at developing applied science because it's a short-term objective. So it's something you can really get in a short time range. You can get results that you can use in some aims, but that is a little bit short-sighted in my mind. And I also think that, and this is why basic science should be funded more, in my opinion, at least. And I also think that this is resulting in an issue related to the idea of publish or perish. Basically, everything should be aimed at a very fancy or very high impact effect of our research, but basic science doesn't work this way. So we need time, we need to produce step-by-step science, also to report failures, because this is still very important. So everything is related to the idea of starting from a basic concept and develop from that concept applied science, which is just a consequence, in my mind at least, of the basic background we need to develop and fund, therefore.
So I understand then that there is the need still to make policymakers more aware of the necessity of basic sciences. So how could we do that? Because it's obvious that we need always policymakers on our side.
Sure. I mean, we need to be able to, on one side, to let them understand the importance of basic science, also to highlight how, I mean, it's not a challenge for everybody to find their way to be the best scientists, to be the highest impact sciences, because this is not something that is helping to collaboration. And without collaboration, I mean, there is no way to develop. We're not all geniuses. We need to work together and find a solution to things. So we need to let the policymaker know that this is a collaborative effort. This is something we all need to do together and collaborate towards the end of developing a step-by-step process to develop new application at the end. But we need time, and we need to really to get to something that has an aim, which must be, for instance, sustainability, but without, I mean, maybe we're studying something that will have no way to get into the real world, but the steps in between to that end are probably going to develop another field that we don't know at the moment. So that is the idea we need to provide also to the community, to society as well.
And do you think these efforts should come from research institutions, universities, or more from journalists, communicators? Because if one needs to reach the policymakers, I'm not so sure if this would be possible only from universities or so. What's your impression?
Sure. So I think it should be really a joint effort. In particular, I think universities shouldn't be too much focused on just published indicators and so on. They should be more focused on the impact of science that is performed by the researcher, and talking about the scientific impact, not only the application and the claim at the end of the paper, but also the process in between. So and obviously, again, the social media and journals are really pushing a lot as researchers towards the end of publishing everything super fancy and everything super nice, but we're losing a lot of information. This will become a big issue as soon as we have, for instance, this artificial intelligence that is developing, and we will need also to have reliable data and also data related to failures to provide a good data set for future studies, which will be based on machine learning and artificial intelligence. So that is an important point.
Mm-hmm. I see you are already working on energy conversion, right? That was one of the breakthroughs that has been mentioned by other colleagues that we interviewed. So what would you like to see as a breakthrough in science in the coming years?
Well, I think there are probably at least one general breakthrough that is, again, related to, as it was already mentioned, to artificial intelligence and machine learning, as this is basically changing our idea of making science or developing new science in the future. So that is a fundamental but very general breakthrough. And the second one, related to my field, I think it's mostly related to the energy storage devices, because we have very efficient conversion devices, we have quite efficient storage devices, but at the present time, we don't really. We're quite at the edge of the technology. We need to find new technology, and to do that, we need to go a step back and develop new basic science to develop new kind of technology. So I think in the next years, the problem of energy storage, which will become the most important problem in energy technology, will be solved by just making a step back, looking back at basic science, and then developing new method and new technologies.
Thank you very much. I would like to invite now Marta from ESRF. Thanks for joining us today. You are working in ID31 ESRF. Can you also tell us something else about you and your research, please?
Yeah, so good afternoon or good morning or good evening, depending on where you're located. So thank you for inviting me. That's a pleasure for me to represent a bit the ESRF, is a European synchrotron. I'm working at the ID31 beamline, which is the beamline dedicated to high energy investigation of buried interfaces. That's a bit like a fancy title, but what we do a lot, we work on energy materials, which means we are working a lot on batteries or fuel cells or electrolyzers, so devices that are, let's say, helping the energy transition that we are witnessing nowadays. My background is mainly on battery characterization, but since I joined the ESRF, I'm widening a bit on one side, my characterization portfolio, so I can look at the devices in different ways, but also like I'm widening my expertise from batteries to other electrochemical systems. So that's a bit my background.
Okay, thank you. So why do you think basic sciences are important to society?
The way I see it is like we have a problem. We are like lost in a forest. And what we can do is just like decide to go one direction and just go straight this direction, just walk in the same direction. This is a bit what applied science I see that is doing. So they just go on one direction. They see that is going well, and that's fine. They keep going on the same direction. What basic science can do is like having a compass and a map and deciding where to go, because we do an experiment, fundamental experiment, and we can say, okay, look, this is going better, but maybe if we take like this other path, then we'll get out of the forest in a better way, in a more efficient way. So for me, basic science is like what we have to do if we don't want to go back to solve a problem, let's say, a bit in a blindly way.
So you're also reflecting the importance of failures, no, as it was mentioned before, to advance in science, no?
Sorry, can you repeat? Because
that you are also reflecting on the importance of failures to also advance in science, no? That was also mentioned before.
Yeah. I mean, also like what Raffaello was just saying, that we need to share also our failures, because otherwise we just keep making always the same mistake, just like different groups all over the world. So it's important to share like not only the good results, but also bad results from which we can learn, and which they don't always, they are not always bad results. Maybe we just need to look at them in a different way.
Definitely. So if we talk about policymakers, what can they do to help research, fostering science, basic science, etc.? What is on their hands?
Well, I think there's like a couple of things that can be done from policymakers. On one side is like recognizing a bit the importance of research, of basic research, and let's say acknowledging the impact that we are having on society. We had like a lot of presentation today on the impact that basic science is having on culture, on arts, on society. So this would already help. The second thing is to I don't remember what I wanted to say, so I got lost, but I think like policymakers, that's what I wanted to say. If they look not only at, let's say, their short-term contract, let's say, so if they look not only at the next 3 to 5 years, but they would maybe make bad decision on the short terms, but which would lead to good decision on the long term. For example, spending money on research might be bad for your political career because you're of course spending money, but on the long term, like your region, your country, it doesn't matter at which level you're looking at, it will get a return of investment that you might not see because it might be on the next political term. So, but these are two things that maybe we should like ask policymakers just to look a bit on a wider range.
Yeah, maybe they should see it as investing in research instead of spending in research.
Yeah, exactly.
Respect for the return to come.
Yeah.
And if we talk about diversity and gender gap, so what can be done to build a more diverse scientific community, not only in terms of gender, but also nationalities, etc.?
So I'm lucky, I'm working at the ESRF, it's the European Synchrotron. So we have we hire people from all over Europe, all over the world. We welcome people from different culture. We encourage people from different background to join us. But it's true that that's not easy. I don't remember who was mentioning the fact that if there are for example, not many girls that are graduating from basic science, from from physics, from mathematics, from these studies, we cannot ask to have like a gender equality at when we are looking at postdocs or at permanent positions. For me, one thing that could help, and one thing that I hope that I'm helping in, is creating like a kind of role models, or like at least to have like to see that there are more people like you that can achieve what you want to achieve. So if there's a young girl that is like that wants to do science and sees someone like a researcher who looks like them from not only gender, but culture, from different backgrounds, different places. And then you see that this person achieved what you want to achieve. Then that would, I think, would help to have a more diverse environment.
Yeah, the importance of role models, of course.
Yeah.
So we are a little bit tight on time, but I wouldn't want to leave without asking for your wishes on the scientific breakthrough. Can you tell us something very briefly, please?
I think we are like making a lot of steps ahead in the energy transition, like how to get rid of internal combustion engine vehicles, like how to use batteries and other energy storage systems. What I really hope that we will be witnessing soon is a way to heal the damage that we did to the planet. For example, with carbon dioxide capture and how to reuse the CO2 to create other chemicals that we can use for biofuels also, for example. So what I hope that we will be seeing in the next years is really like devices that will be able to capture CO2 and that we will be able to really heal our planet.
Thank you. Thank you very much. I want to thank you all and all the participants in the very short interviews that were also very inspirational. And now we are going to have two speakers from the European Exfel facility that are going to tell us about how large-scale research facilities contribute to basic science and to achieve sustainable development goals, and why solving scientific questions require multidisciplinary teams. The first speaker is Chris Milne. He is the leading scientist and group leader of the femtosecond X-ray experiments instrument, FXE, at the European Exfel facility. He received his PhD in physical chemistry in 2006 from the University of Toronto on the topic of ultra-fast nonlinear Raman spectroscopy on liquids. Prior to joining the European Exfel in 2021, he worked on the Swissfel Exfel project at the Paul Scherrer Institute, where he designed and brought up into operation the Albra experimental station in 2017. Chris's research is focused on photochemistry, physical chemistry, and chemical biology, and he is also interested in using advanced X-ray techniques to probe the ultra-fast electronic and structural dynamics in photoexcited molecules, proteins, and materials. And today he is talking about interdisciplinary research at the European Exfel, a team effort. Welcome, Chris.
Thanks very much, Christina. So first, thanks very much for organizing this event. It's quite an epic endeavor, and good afternoon, good evening, good morning to everyone. I'm going to introduce a little bit about what we do here at European Exfel and set it up then for Stefan to continue on how our different processes and systems require a lot of teamwork and how to maintain sustainability throughout the focus of our operation. So here's the introduction. On the bottom right here, we actually have a picture of the facility, and so this is a picture of the building we're actually in right now, and we're located just outside of Hamburg in Germany. Now, the facility itself is actually several kilometers long. And so we start where we generate our electrons in Bahrenfeld in Hamburg proper. And this is led by DAISY, the synchrotron radiation, German synchrotron radiation research facility there. We then propagate the electrons and we accelerate them up to almost relativistic energies. And then we use them to generate photons. And so we use them to generate X-rays in this case, both soft and hard. And you can see that we're located down here in Schenefeld. And this is then in actually a different state of the German Republic. And so we're in Schleswig-Holstein. And so you can see we go underneath the suburbs of Hamburg. And this is quite a large scale project. Now, the goal of the facility is to generate ultra short, ultra brilliant X-ray pulses for researchers to use for their experiments. So we are a user facility, as has been mentioned during some of the previous discussion points, which means that we work closely with international researchers who come here to do experiments. And so this means that week to week, we're doing all sorts of different science, and we measure with all sorts of different countries. We're a European facility, which means we're funded by these countries down at the bottom here. And the goal is, of course, to try to do world-leading research in a variety of fields using the different unique aspects of our facility. And one item I'd like to highlight is this so-called burst mode. So we come through with several hundred pulses separated by about a microsecond. And then we have a long gap in between these bursts. And this allows us to deliver an enormous amount of average X-ray flux. So on the order of 10 to the 14 or 10 to the 15 X-rays per second. And per pulse, we're generating on the order of about 10 to the 12 X-rays. And so for a lot of measurements, this is an ideal source. And so we get research coming from physics, material science, chemistry, biology, geosciences. Week to week, we work with a broad range of different kinds of researchers from all over the world. And we're a relatively young facility. So we got our first X-rays in 2017, and we had these different branches come online. We generally measure on 3 different branches of the accelerator. And so this means that at any given moment, we have 3 experiments running with our colleagues and collaborators. We cover the range from the soft X-rays. So this would be, say, a few hundred electron volts out to very hard X-rays, 25 keV, which means that we can do research looking at a variety of different elements in the periodic table, from carbon all the way through up to molybdenum. And because we can work simultaneously with these three different branches, we can also host a number of different parallel experiments. We have a number of instruments that are then installed on the facility. They cover a broad range of science. And so I'm not going to go into significant detail here for these different instruments, but we measure ultrafast dynamics. So we look at very fast timescale events, usually initiated by a short optical laser pulse. We do single particle imaging, where we focus the X-rays down into very small volumes of space, and then we scatter off of material science or biological targets. We do a technique called X-ray photon correlation spectroscopy, which looks at the changes between the scattering events from our coherent X-ray beam from pulse to pulse. We do high energy density, and so this involves compressing or exciting materials into very non-equilibrium states, and then using the X-rays to probe this. We do soft X-ray nonlinear spectroscopy. So we take advantage of the fact that we have very short and very brilliant X-ray pulses to excite states that are not normally accessible from continuous or less intense X-ray pulses. And we do a fair amount of soft X-ray measurements on ultrafast dynamics. We also have a new instrument which focuses on doing experiments using techniques such as angular resolved photoemission spectroscopy. And so on the whole, you can think of the European XFEL as providing a broad range of different measurement techniques and different sample environments to study all forms of different research. Now, I'm going to highlight a little bit the instrument that I work at, the femtosecond X-ray experiments instrument, just to give you a sense as to the scope and the scale of these different kinds of experiments. This is a 3D model of the inside of the X-ray hutch, and it's meant to just give you an overview of the complexity of the different systems. So the X-rays come in from the right. They go through a number of different elements to focus or attenuate or to measure the X-ray beam. We focus them then onto a sample, which could be a solid or liquid, and then we probe it using the X-ray tools that we have available, including large detectors or spectrometers. And we also have access to a broad range of laser wavelengths to photoexcite the sample. And so this is the sort of environment that you would take advantage of were you to come do an experiment here with us. And just to emphasize the complexity, this means that for any given measurement, we require control over the sample environment. So we could potentially require vacuum, or we could require helium or a neutral environment, oxygen-free, for example, for chemically sensitive samples. We work with liquids, we work with solids, we work in transmission geometry, which is what this movie is showing, where we shoot the X-rays at these thin metal films and destroy them, and we make the measurement before the destruction occurs. We need sophisticated X-ray detectors to measure the X-ray pulses as they come out of the machine. We need online data analysis. We need X-ray spectrometers with large degrees of motion control. So each one of these spectrometers requires about 20 or 30 degrees of motorized freedom. And then we need to synchronize it in order to be able to change these things all simultaneously. And then we need a broad range of laser excitation in order to control and to excite the different kinds of materials that the researchers are interested in. And so this is meant to sort of give you a sense as to the complexity of the kinds of environments and systems that we use routinely here at the European XFEL. And we also then need a large amount of people who can be experts and who can take advantage of these various tools in order to do their research. And so we have a broad range of postdocs and PhD students, engineers and technicians and scientists. And of course, we worked very closely with a large number of groups at the facility. And so you can think of this as being a very team-oriented operation. And so week to week, then our team will dynamically include researchers from around the world. And we make measurements such as scattering. So we look at X-ray diffraction or scattering off of solid state materials, usually to visualize dynamics, to follow the atoms as they move or the charge distribution in these materials. And we do a fair amount of biochemistry and chemistry systems, where we're looking at changes in molecules or changes in proteins as they function or after they've been light activated. And so all of these things are then done on the order of femtoseconds or picoseconds, which are the timescales on which electrons and atoms move in these kinds of materials. Now, here are some examples of the kinds of large-scale challenges that we're addressing with the broad range of research we do at the facility. And so one topic, which is obviously of importance to human health and life, is water and access to clean water. And so one of the systems that we measured last year with Julia Weinstein's group from the University of Sheffield was a photoactivated antibacterial agent. And so this is a copper molecule that you can put into solution. And when it absorbs light, you create singlet oxygen, which is then destructive to the bacterial components of your mixture. And so in order to understand exactly how this system works when it absorbs light, Julia and her team came to the facility in order to measure what was happening both in the structure and electronic environment of the copper atom after it absorbs light. We also do a fair amount of geology and geochemistry. And in this particular case, the goal was to investigate the conditions that are found closer to the center of the Earth. And this is to look then for iron molten cores and how they behave under high intensity excitation and pressure. And so the goal was to reach regimes of the phase diagram that aren't achievable elsewhere, and to take advantage of the high per pulse brilliance of the XFEL in order to probe these very transient states in order to understand what's happening at the Earth's core. We've also measured some insecticidal properties. And so this is a bacterial insecticide, which is in routine use for agriculture and medicine. And in this particular system, what happens is that it grows crystals within the stomach of the insects. And when it does this, then this is obviously destructive to the insect. And in order to understand how this process occurs, we did crystallography and protein crystallography on these naturally occurring nanocrystals. And so the goal was to try to understand how this process happens and how these systems form within the proteins that make up this bacterial insecticide. This experiment here was to probe the dynamics of ionizing radiation in water. And so in the upper atmosphere, where there's a significant dose of UV and high energy photons, you can create these radical states where you have unpaired electrons. These are very reactive. And so you can create a broad range of photochemistry, some of which you'll be aware of, for example, with the ozone layer and the various chlorofluorocarbons that were creating holes in it. And so the goal of this experiment was to understand how this ionizing radiation interacts with the water and exactly then how it behaves when we create these radical states. And so in this, the goal was to measure coincidence charged particles of electrons and positively charged particles in order to better understand the fragmentation and the intramolecular dynamics of the water molecule when it breaks into pieces. And of course, this is occurring on very fast timescales. And so these elements are very light. And so you're looking for sort of femtosecond dynamics using your X-ray techniques. This is an example of a G protein coupled receptor, which is a protein that's found in the cell membrane. And these are often very reactive sites. So they are drug targets and they control a large amount of biochemistry. And so the goal was, in order to understand how these systems function, to perform crystallography on them. And this was a collaboration between the Sosei Heptares company and the European XFEL in order to measure the structure of one of these GPCRs. And the interesting feature of GPCRs is that they do not form large crystals. And so they are not capable of being crystallized into large-scale crystals in order to be able to measure them, for example, using other techniques. This is an example of greener and more sustainable energy solutions, which was looking at a cobalt oxide crystal. And in this material, when you shine light on it, either blue light or red light, you get different excitation processes and you get different chemistry. And so the idea then is to understand how these photoexcitation processes affect the photochemistry and the catalytic properties of this cobalt oxide material. And this was done in collaboration with Giulia Mancini at the University of Pavia and Majed Chergui at EPFL. Now, we're also interested in various kinds of magnetic materials. And so in this case, the material in question was an iron platinum mixture with very small domains. And this particular mixture, when you excite it, when you photoexcite it, you launch a spin wave in the material. And so the idea was then to probe this spin wave dynamics and to understand exactly how you're changing the spins in these different domains after photoexcitation. And so, of course, this means that you're working on very short and very fast scales. And so the concept is to understand how these materials function on an atomic level in order to be able to take advantage of them for future generations of storage devices. And this example here is to look at energy transport within strontium titanium oxide, which is a large bandgap semiconductor. And in this particular case, when you make the very constrained sort of large-scale volumes of this material, you start to get interesting properties of it. And so the goal was to try to understand how the electronic excitation of this material propagates through it, and then also how to understand how heat transport is dissipated within it. And so you can see that in the example here, we have very short timescales, and we can see some structural dynamics which are occurring. And so the goal is to try to use this information to understand exactly how energy moves through this kind of material. So with that, I will wrap up and just mention that X-rays are clearly a very powerful tool. They complement your lab-based sources. They complement a range of different measurements which can occur on different kinds of materials. And they're excellent at probing structure and probing electronic degrees of freedom in all sorts of different kinds of materials. In order to do these experiments, we need a large team, as shown here from the staff photo of the European XFEL. And in order to work efficiently together, this means we need to work well as a team. And we need to have efficient and reliable tools. And so the goal of obviously is to host researchers in an efficient way so that they come, perform their experiments, and then leave with their high quality data in as efficient a process as possible. And we're focused then on benefiting society through fundamental research or basic research, technology development, since we're really working on the very boundaries of technology, and also training young researchers. And so with that, I'd be happy to enter into any discussion or answer any questions you might have before Stefan takes over.
I actually have a question. You have showed us that there are many different experiments that can be done on XFEL, no? But imagine there is a group that performs certain research, and then they think they can use XFEL for their experiments. So how can a group that never did any experiment at XFEL can start preparing? What do they have to do?
That's a really good question. So the simplest thing to do is to contact us at the European XFEL. And so to get in touch through the webpage is the most straightforward way, and then start the discussion. And usually we can guide the researchers in the direction of understanding whether our tools would be appropriate to answer the scientific questions that they have, or perhaps to connect them to our colleagues, for example, at ESRF or at DAISY or at ultrafast laser labs, or using other methods to characterize their sample in order to help address the science that they would like to resolve. And the ability to perform experiments at an exfil is challenging. And this is why having the support and the well-trained staff here is a significant benefit for researchers.
And thinking about their samples, there might be some differences. So how they use or produce their samples, and they usually characterize them at their labs. There might be also a transition or an adaptation period on how to treat samples to be useful for
Yes, that's definitely true. I mean, as you can see with the one video there that popped up, the ability to destroy the sample is crucial. And so if this is something where, you know, you have a limited amount or you have a small volume of it, then this is something where we would need to understand how best to deliver it into the beam to perform the measurement. The measurements themselves are often well defined, so we understand whether they should be in solution, or they should be a thin stream of crystals, or they should be deposited onto a thin film. And each of these things is something that is part of the process of identifying how best to do the experiment. And so this would be something that would occur naturally as part of the discussion about how to perform an experiment at the European exfil.
So the message to go is that it's crucial actually to contact the scientists at exfil to start discussing how to accomplish an experiment.
Yes, definitely. And we also are trying, I mean, we're engaged. In fact, Stefan is leading this. We're engaged in a large amount of outreach and discussions with various research communities. And so the idea of trying to get a discussion going in person at your host facility would also be something that would be interesting. But the definite message is that we should just start a discussion to try to figure out what the best approach is to perform experiments.
Definitely. Thank you. Then I will go on with Stefan. Stefan Hauff leads the control software group at the European exfil. After completing his PhD in astrophysics at TU Darmstadt in 2012, which focused on Monte Carlo simulations for space-based X-ray observatories, he started as a detector calibration software scientist at the European exfil. Following a temporary appointment of interim technical lead for the in-house development Carabo control system in 2016, he co-developed the facility's initial detector calibration tool chain. In 2019, he shifted his focus back to control systems, joining the controls group as lead of the instrument integration team, before he became group leader in 2021. His areas of expertise are scientific control systems, hardware integration, collaborative software development, and agile management methods. Through his previous work, he additionally has a background in X-ray detector calibration and high-volume data processing. The title of his presentation today is Interdisciplinary Approaches for Better and Sustainable Software at the European exfil. Please, Stefan, go ahead. Thank you.
Thank you, Christina, for the introduction, and also thanks, Chris, that I don't have to give a general introduction to the facility, and that you've already highlighted the complexity quite a bit. So given the many time zones we're in, I'll just say good day to everyone. And about halfway through the presentation, I think you also have an idea what this piece of modern art on my first slide is. I do want to give a little bit of a motivation, though, why software is important. First, maybe very generally, this plot here shows you on the x-axis time, and on the y-axis, the relative peak brilliance of modern light sources, X-ray light sources, and the number of transistors and processors, so commonly known as Moore's law. And the y-axis here is logarithmic, so this is actually both exponential, and you can see they're decoupling a bit. And if we now kind of naively assume a bit that every photon we generate here could be a useful point of data we want to process, you see where this is going. Just throwing more hardware at the solution might, throwing more hardware at the problem might not be a solution really anymore. So specifically for the European exfil, if we stay with the data perspective, we've produced so far around 100 petabytes of data. That's 100,000 terabytes. That's quite a lot, and maybe a good unit to visualize that is actually USB hard drives, which nowadays frequently come 1 terabyte in size and are about 1 centimeter tall. So if you stack these things up to reach 100 petabyte, you have a 1 kilometer high tower. That's a lot of data. And processing this data, acquiring this data, software is needed to make that happen. For us specifically at the facility, this means our software can produce up to 5 petabytes of data per week. Luckily, the instruments, which Chris just showed, don't regularly do all that much. Otherwise, we might run out of hard disk space. We can also run our software on a large computing cluster, actually at DAISY, with up to 10,000 cores and hundreds of GPUs. So given these numbers, and now I'm going to switch a bit over to sustainable software engineering, can actually make a difference in the facility's environmental footprint. Not to mention here that better software usually also gives better scientific advances in the fields Chris mentioned, like biophysics, like material science. So when I say software, what does this mean for a facility like the European Expo? Well, you've got maybe at the basics, the control software firmware, things which control your detectors, your vacuum components, all that. Then you want to somehow acquire the data you're measuring, so you have data acquisition software. You need to process that data, so ideally at some point you get a figure which you can put in a report or publish in a paper or put on the web. And you have procedures which coordinate all that, so a human doesn't have to click too many buttons. If we look at the European Expo code repositories alone, we definitely have more than 400,000 lines of code in there, which is in active use and being maintained. You can also see that in the fact that at the facility, there's approximately 50 people out of 450 staff in total who are specifically tasked with writing software, some of which, for instance, in the group I lead. Okay, now one more definition, and then we go on to a few examples. What is sustainable software? So disclaimer here, I am not an expert on sustainable software engineering, but I can read definitions on the internet and then compare them against our software, which actually is quite a nice exercise to do. But generally, sustainable software should be efficient. That's maybe kind of obvious, and also make efficient use of hardware. So you don't need a supercomputing cluster to read or write an email. Sustainable software should prolong the useful lifetime of existing hardware. So it should not only need cutting edge hardware. That's, by the way, very expensive as well. To be exact here for European Expo, the useful lifetime for really production hardware, so where we take measurements, is usually kind of limited a bit by the warranty, which is 3 years, but we then don't just throw that away, but we use it for less critical items afterwards. And finally, it should be efficient on the network and in terms of storage, so you don't send unnecessary data out. So these definitions I took from Microsoft. I'll add one of my own. It should also be sustainable for humans to use and develop and maintain. A little bit more on that later. Good. Let's show some examples. One here at the facility, which is developed in the controls group, is our in-house distributed control system. It's called Kalabu. And you see on the sketch a bit on the right what a distributed control system can look like. For us, it's a message-based system working on a so-called central message broker. That's that purple thing here in the middle, always shown as a cylinder. And that basically receives messages from different components in the environment and dispatches them to where they need to go. So if a camera wants to talk to a logger, it will take care of that. For really big data, you don't usually want to use such a broker. For that, we have high bandwidth point-to-point connections. So camera talking to some image analysis maybe. Importantly, we use that system for remote control and monitoring of the equipment at the facility. Or in another word, it keeps humans out of the X-rays way, so out of the hutches, and makes the experiments running and manageable. One additional feature of Kalabu is it's event-driven. And you see that at the plot here on the right of the sketch. A more traditional system would poll this data. So maybe once a second, it would take a measurement. An event-driven system really only sends data out when a value significantly changes, so the orange points here. So what scope is that about? Well, the European Expo, that control system contains about 2.5 million control parameters. And now we're at this modern piece of art. This is actually a rendering of the control system topology of our MID instrument. So the points here are pluggable software components. The lines are their interconnections, things that talk over this message broker. And the colors represent different application classes of the software. So this is actually highly complex. And through the remainder of the talk, I want to motivate, amongst other things, a bit that interdisciplinary teams help us manage this complexity. The next slide highlights a bit more what's actually going on with the network, but it's a bit of a flashy video. So if you have discomfort with flashing videos, I'll tell you when it's over and you might not want to view this one. But for those who do, here's what I call Caribou broker pong. So on the left side, you have things sending data, on the right side, the receivers, and this is in real time. Okay, this is recorded, but actually time flow is as in real time. And you already see that's quite a lot. If now we had a polling system and everything just sends up once every second, you're at even more. So if we now check Caribou against our sustainability checklist, I guess somewhat on accident, where we actually developed a quite sustainable system there. So the data is only sent over the network when it actually changed, because it's event-driven. So that's quite efficient on network and storage, actually. Turns out the system was also highly scalable. It can run on hardware as small as a Raspberry Pi, or on systems with tens, of course, and we're doing both. And it's also within the limits, which you, of course, need to maintain, able of saturating either of these systems. So it really maximizes the usage of available hardware, and can also run on older hardware. The system itself is extendable, so you can add more pluggable software components to a core system. So it can also accommodate new requirements and grow as you need it. And then the user interface is actually, our scientists can quite easily adapt without needing coding. So that's also bit on the sustainable side for humans. We've early on seen Anna, who works in the group actually on coding GUIs as well, which can be more specific then, but it offers both solutions. Caribou is also well tested. On the right side, you see Anya, who's our dedicated test engineer. And this is really important. The machine and the instruments Chris showed you earlier, they consume a lot of energy on their own. For the accelerator, which is cryogenic, superconducting, we're talking decent town, actually, in terms of energy consumption. So if this is running and a piece of software fails at the other end and you can't actually record any data, this might all go to waste. So Anya, for instance, here has more than 6,000 test cases she runs through at every release to make our software reliable and stable. And one additional thing we do there is we actually follow coding standards and have a mandatory code review process, which makes our code maintainable. So who does all that? Okay, you've already seen Anya. Here's the rest of the group. We're pretty interdisciplinary and also diverse in where we come from. So we have colleagues from 11 different countries. These little symbols show a bit on the background, which is anywhere from software engineering to nuclear physics. I'd say we also have a strong cultural diversity, given the number of countries. However, as you can also see from the picture, we should be honest that gender diversity can still be improved. And what Monica and Marta said there earlier on in the interviews, I think it's really important to start early here. So high school and university, to show young people that a profession in software engineering at a facility like ours can be both interesting and also achievable. Because of our cultural diversity, we also chose to adopt the Google style guide to avoid marginalizing language in our code and our documentation. One important aspect of working together in such an interdisciplinary term is what I've mentioned before, is code review. You see a screenshot there from what is a tool called GitLab, that's a web tool, where we have discussions on how code is changed. And no code can go into the reference code database without such a discussion happening. That's actually quite a lot of things being there discussed. So I pulled out the number of words and comments from 2022, which is about 350,000. And if you look into works of classical literature, we're somewhere between Moby Dick and Ulysses there in terms of words written and comments there. Good. Another example where software can help in terms of sustainability, that is predictive maintenance. So if you look at the plot on the lower right here, which is an arbitrary sketch of some data coming in our time series database. And what we're aiming here is to predict future trends and maybe identify that something might fail or an issue might occur. If you get that early on, you could in the best maintain hardware, for instance, before it fails, or at least swap it out before it fails during operation. Again, think of the accelerator and everything. This all draws a lot of power, so let's make use of it. The effort here is mainly in the data analysis group, and that's Anna and Danilo, you see on the top right. We're working on models and methods to analyze the data relevant for our control and vacuum systems. My final example in terms of software actually is detector calibration, which I actually kind of started off with at the facility. And maybe you saw that LPD detector in Chris's slides from the FXE instrument. So That's the one-of-a-kind detector with very high data rates. We're talking 20 gigabytes per second. And the images you get out of it, well, you can distinguish something in this raw image, but you actually need to do calibration corrections first to get the most out of it and do actual science. And this is our main data product. So doing this successfully really critically impacts the quality and of the data and the science we do at the facility. If we look into that a bit more detail, we get this sketch. That's how the thing is set up. You see the detector again here on the top left. And then this goes on a bunch of huge hard disks. And then there's basically two ways for the data to go on. One is what we call offline processing. That's that huge computing cluster. Or to online processing where you want low latency and actually see what you're doing. And you need, for both, you need this calibration database to provide calibration constants and then appropriately correct the data. This online processing, by the way, will be important, the low latency for a final example I give. Now, if we look at the team doing this, which consists of basically 3 different groups here. So we have data analysis, IT, data management, and detector represented. We really need experts on the scientific and engineering domain. We need detector scientists who know how these detectors behave, what is appropriate to do in calibration, how the algorithm should generally look like. And then we need software experts and IT experts who can handle the high data throughput, who write algorithms which can actually do these operations at 20 gigabytes per second. Okay, one more example, and this one's away from actual coding, but also a very good example of interdisciplinarity and agility. And that's the support model we have for the data department, where the groups I've mentioned before are all in. And that's what we call the Data Operations Center, the DOC. And this center really gives support for the control system, data processing, detectors, data analysis, data persistence, all these kind of issues. And there's 2 department members on shift there, and they're from 2 different groups by design. They should also be from 2 different groups. So we have interdisciplinary expertise, but nobody's an expert on everything. So we also have second level on-call experts who back them up. And as I said, by design, this is an interdisciplinary effort, and it's created and sustained through agile methods. And maybe to highlight this a bit, this is an incident I was involved in myself. I call it the mystery of the broken fiber. So here we're again talking one of these large bespoke detectors for the facility, which is critical for the SPB instrument. It's their main detector. And I want to draw your attention a bit on that small plot here in the center. Things should look like how they look like on the right side of this plot. The x-axis here again is time. We're looking at our time series database, and the y-axis is latency in seconds. And that should usually be well below 1 second. But what we observed in the Data Operations Center was this jitter you see on the left. So we call the instrument, iterate the settings, there's nothing apparently wrong. So that's where we really start monitoring it. At first it went on quite okay still, but then somehow we see that writing data to disk and seeing what is happening has become mutually exclusive. And that's not so good if you have a detector, which is worth millions in there, and an X-ray free electron laser, which with a few shots can burn through that detector. So we start calling second level support experts, and at some point we actually have IT sees that there's a bottleneck in the network. And it turns out this was a broken fiber, and then somebody went into a server room, unplugged that fiber, and the network automatically reconfigured itself and avoided the issue. That's a really good example of an interdisciplinary solution to a highly complex problem, which occurred, I think, within 1.5 hours of it occurring, so quite quickly. Good. So I'm not yet fully done, but I have a conclusion so far, because it seems like interdisciplinary groups do kind of excel at creating scalable and high quality software in scientific research contents like ours. And maybe one could facilitate such groups a bit. And one way of fostering this is agile development, in my view. So in software development, you have established agile approaches such as Scrum or Kanban, which contrast with waterfall models. Agile, much decision is left up to the team. You have rapid increments, feedback cycles, as you see in this sketch. And you basically try to deploy something in rapid succession and get feedback. Waterfall, most design decisions are taken beforehand and documented, and then the team really literally works through as like a waterfall of tasks sequentially, as you see at the bottom. If we give a bit more detail to that, or the benefits. So Agile ideally empowers the team to out-of-the-box thinking and encourages testing of ideas. There's another sketch, if you translate that somebody seeing a steam locomotive and somebody else pointing at a rocket into software, that's basically somebody pointing out, hey, maybe somebody already did this from the community and maybe we should be using that instead of reinventing a square wheel. And you have the rapid feedback cycles, which give feedback into the system. Waterfall, you might be tempted that leads to more consistent design, but frequently it actually also yields consistent anti-patterns or even the dead end, a bicycle with square wheels, for instance. Also, by the time something has gone through the whole chain, it might be outdated. Waterfall can be the right choice for certain scenarios, like if we're talking safety, for instance, but Agile kind of lends itself well to our environment. In Agile, if we got something wrong, we know after a month, hopefully, when showing it to the scientists. If we got it wrong with Waterfall, we might have put a year effort in it. At XFL, we basically use a variety of these processes. Frequently nowadays in the controls group, it's Kanban. You see the Kanban board from one of our teams here on the right. What's important here are that the tasks are small, they need a definition of done, and in principle, any team member is entitled to take tasks. Think again, interdisciplinary people learn while doing this. Teams might also change from sprint to sprint. So these are increments of maybe 2 to 4 weeks, which facilitates exchange and new views on the problem. And finally, the feedback rounds include other shareholders, like our instrument scientists, which reduce the risk of confirmation bias, where you really think this is awesome what you just developed in terms of software, and then you give it to the customer, and they're like, well, that's not what we asked for. And this feedback happens more often. So does staff appreciate that? This is my last slide before the summary. We did a survey of people in the Data Operations Center, and I won't go through all of it, but the central 3 are important. The further bars to the right, the better or more approval this said. And we asked people if they learned new things and if it improved communication, and that actually happens. So this is one way of developing staff, actually. In summary, seems like interdisciplinary groups really excel at creating scalable and high quality software. And if we use modern technologies and concepts, they might even be sustainable. We should, of course, keep in mind that facilities like European XFL generally have quite a high environmental footprint. And what I didn't mention in detail, much of the software we develop at the facility builds on community established libraries and tools. So the use case might be XFL specific, but how we get there often is not. Thank you.
Thank you, Stefan. So I was actually going to ask you something that you just mentioned. So all the control software that is developed here at XFL is not specific. So the knowledge can be transferred if you know, if the engineers or scientists go elsewhere, or the scientists.
Well, I think some of the end software products might be very specific to what we need, but the way of getting there, the building blocks they build on, there we use many community provided tools like the time series database I mentioned. That is what is called InfluxDB. That has wide application cases. So I think people get trained on many more fundamental technologies in the process, which can definitely be used at various other scientific facilities or in industry.
Mm-hmm. Okay. Thank you. So I thank you both, Chris and Stefan, for your contributions. Very interesting, both of them. And now we are going to move on for the panel discussion that is going to be moderated by my colleague, Dr. Anita Chandran, that is specialist in communication.
Hi, everybody. Good afternoon. So I'll start by sharing my screen. Okay. And then I am going to introduce each of our 4 panelists for our panel discussion on gender equality, improving gender equality in sciences. And then I will hand over to Professor Marie-Françoise Roy, who will give you some context, and then we'll launch straight into some questions to each of the panelists. So to start, Professor Marie-Françoise Roy is an emeritus professor in mathematics in Rennes, in France. She was awarded the Prix Irène Joyaux-Curie in 2004 and became Chevalier de la Légion d'honneur in 2009, and Officer de l'Ordre National du Mérite in 2014. She is the first president of Femmes et Mathématiques from 1987 to 1989, and she has been the convener of the European Women in Mathematics organization from 2009 to 2013. She was the first chair of the International Mathematical Union Committee for Women in Mathematics from 2015 to December 2022, and was one of the 2 leaders of the Gender Gap in Science project funded by the ISC from 2017 to 2019. She's also the representative of IMU, the International Mathematical Union, at the Standing Committee for Gender Equality in Sciences, as well as their communications officer. Professor Yvonne Bonzi Coulibaly is professor at Joseph Kizerbo University in Ouagadougou in Burkina Faso. For over 30 years, she's been involved in teaching organic or environmental chemistry, developing research activities and managing projects, all converging on local biomass chemistry and applications applied by women farmers for botanical pesticide production in a microbiorefinery. Professor Bonzi Coulibaly has been director of the Center for Environmental Studies, Research and General Director of the Institute of Sciences. She is involved in scientific communities at both local and international levels and has established conferences and workshops on research themes for the benefit of scientists. She was laureate of the African Union's Kwame Nkrumah Prize for Women Scientists in Basic Research, Technology and Innovation in 2013, and is a founding member of the National Academy of Sciences, Arts and Letters of Burkina Faso. Melania Coletta is formerly an accountant and then human resources professional. Melania spent several years prior to her current role at CERN at the European Central Bank in Frankfurt. She's also worked in the private sector on projects accessing European Union funds for women, vulnerable populations, and other needs within specific industries. Coming into the diversity and inclusion portfolio at the European Central Bank turned a job assignment into a passion for her. Inspired by the possibilities and motivated by positive change, she's chosen to remain within the diversity and inclusion environment ever since. Her favorite motto is "Diversity is fact, inclusion is an act," and she has since joined CERN in April 2022. Her philosophy is to drive and implement as many acts of inclusion as possible within the workplace. Dr. Fan Yu Zhen, the last of our panelists, holds a bachelor's degree in psychology and a master's degree in biomedical sciences from the Université de Montréal, as well as a PhD in psychology from Stanford University. After her graduate studies, she joined Concordia University's psychology department as a lecturer, a position that she held for 3 years before moving on to work as a research associate in neuroscience at the Université Laval. In 2016, she joined the Fonds de Recherche du Québec, the main research granting agency in the province of Quebec, as part of the strategic planning team. In that role, she served on the organizing committee for the Gender Summit 11 in North America, which was held in Montreal in 2017, and on the steering committee for UNESCO's STEM and Gender Advancement project in Quebec. In 2019, she became the FRQ's first strategic advisor on equity, diversity, and inclusion. So those are our amazing panelists for this afternoon, and I will now hand over to Professor Roy to give you a little bit of information about some context on the International Year's actions on gender equality in the sciences.
That should be better. Okay. Okay, many thanks for the invitation. So I've just prepared very few slides to present the context. Yes. So as was mentioned, we have this very big international and interdisciplinary project called the Gender Gap in Science, which took place from 2017 to 2019, and it was involving 11 scientific organizations, basically international unions in various sciences such as physics, chemistry, mathematics, and so on, and astronomy. And it was a project supported by the International Science Council, and you can find the website of the project here. Okay, so next. So in fact, what before. So at the end of the project, sorry, the one before? Yes, no, yes. So at the end of the project, we were able to produce a book, which is called the Gender Gap in Science book, and it's reporting on the three aspects of the project that we worked on. One was a questionnaire, a survey, global survey of scientists, where we got more than 30,000 answers all over the world. And the other was some data analysis of publication patterns having to do with the proportion of women publishing in various aspects of science. And the third one was a study of the best practices that people had suggested to improve the gender gap in science. Okay, next. So this book, in fact, is
Marie-Françoise, sorry to jump in, but I think your microphone is having a little bit of distortion.
Yeah.
Could you potentially try coming off the headphones? Maybe that will help.
This is better?
Yes, I think that is better.
Okay. Okay, thank you. Sorry for that. Okay, so this way is good, right? Okay, thank you.
Yes.
Okay, so I wanted to mention that after the book was finished, we also created what we call the Gender Gap in Science booklet, which is a summary of the project in 8 pages in several languages, and they include 4 pages of recommendations that we think are good initiatives to reduce the gender gap. And finally, I wanted to say, so next, that we created also some permanent structure at the end of the project. It's what is called the Standing Committee for Gender Equality in Science, which is part of the International Year for Basic Sciences and Sustainable Development. And this committee is organizing a webinar, which is widely followed, and also organizing an annual report of all its members. So there are more than 20 members now, which are international scientific unions, and they work together in order to see what are the best initiatives and the best practices that they can share in order to reduce the gender gap. So what I wanted to say that in spite of many efforts, the gender gap in science is very real, and women are underrepresented and discriminated in several ways all over the world in all possible scientific disciplines. Maybe in some disciplines there are very few women, even inside the population who study the science. But in other sciences, the women are very many to start with. But at the end, when you look at the top levels, I mean, say like full professorship or international, for example, being leaders of international unions and this kind of thing, you see that the proportion of women becomes very, very small. So I think it's a very, as many people mentioned already, I mean, I was attending the last session and many people mentioned the importance of diversity for basic sciences and also of reducing the gender gap. So it's really a problem which is very universal and very important for scientists. So I think what's important is to work at an international level and to work also at the interdisciplinary level. So every initiative in this spirit, I think, is quite useful, and it will take a long time to be able to reduce entirely the gender gap in science, I guess. So that's just what the few words I wanted to say to give the context. So there are some links, like the book I mentioned. The link was not visible, I guess, but it's on Zenodo. So Zenodo, which was developed by CERN, as we've been learning earlier in the afternoon. And so it's really available. All of what we are doing is freely available on the various websites. Okay, thank you.
Saz. So we will now start the more panel part of the discussion. I will actually take us back so we can be reminded of who is speaking to you. And I'm going to start by asking each of the speakers in turn to give a short introduction on kind of what policies they know of in place at the moment to address gender equality, specifically either at their institutions or more generally in the general public. So we'll start with Yvonne Bonzi-Coulibaly.
Okay.
Maybe should I stop sharing then?
Everybody, and thank you. So I can take my time for my talk. It is that. Okay. So in Burkina Faso, where I am, in West Africa, gender inequality is the same like in other countries in developing countries. There are common reasons, well-known reasons, and due to social and cultural obstacles, many girls are fully excluded from education because they are more affected by some household work, some family duty, some early marriage, some pregnancy, some child care. So it's difficult for them to reach high-level education. In my country, 1 girl on 10 married before her 15th birthday. So the government have some incitative policies. I can cite few of them, which are very important. Since 2017, girls' quota exists for admission in high school. And also, these high schools are like excellence centers for science education in secondary school. Also, for new bachelor, there is a quota about 300 scholarships for girls to be at the university. And also for the doctoral scholarship, we have some facilities about the age. When the limit of age is 22 for men, it is 24 for girls. This is very good. And also the average for the must have 11.5 for girls toward 12 for boys. So despite all these facilities, the situation are always very difficult. In my university, we have about 14% of female teaching in our university. So me, I think that this parity is due to the fact that the action must reach the secondary level. It is at the secondary level that we have to make a high sensibilization of people to help girls to reach high level of education and to choose also science for the education. There are many activities, but I just want to highlight the importance of a panel. I am actually in a panel. I think this event is very important because it's easy to organize. And I believe in the world of a woman, we have to choose local women who have, in the same context, succeeded to their career, succeeded their studies, and also have a family. So this example is, I believe in the work of this kind of ladies who succeed despite all the difficulties in local situation. So the academy organized by moment some panel with physicians, chemists, biologists, so on. And I think it is very important to show pictures of this model, this woman self, and because their work can speak to the parents, to the students, and to all the communities. This is my first word for the moment.
Thank you so much, Yvonne. That's very powerful, I think, to believe in the word of women is a really, really great thing to hear. I will then pass on to Melania Coletta to continue.
Thank you, Anita. Okay, so I'm bringing today to the table a different perspective, which is the one coming from CERN. CERN is not an institution, although we work in science. We work in science, but we are not academia, although we feel a bit like academia. Currently at CERN, we have different policies in place to address issues surrounding gender inequality. We start from the very beginning. We really believe that it starts at school. It starts maybe in primary school. There is a research saying that girls go away from science between 8 and 10 years old. So at CERN, for example, there is an outreach program that goes to teachers in schools and enhance their way of teaching science. Later on, we are, for example, allowing now some of the departments at CERN, they allow their people, when they fly back home, to go to their schools of origin, to go to talk to the students of those schools and to promote a career in science. With, of course, there is a focus on girls in science. We have different programs at CERN, like for students, for grads, for PhDs, etc. So we try to accompany them throughout their patterns, but as well as we also have, for example, a career break fellowship, which is a returnship program for a women, for example, that had interrupted their career for a certain amount of years for X reasons. Most common reason it's motherhood, and then they want to return to a career in science. So those are a bit the programs that we are offering, and we believe in this way we are supporting the community out there, the science community. Of course, we do high energy physics, but it's not only physicists at CERN. We have a lot of engineers and a lot of people in STEM. Last but not least, I would like to say that 2 years ago, for the first time at CERN, we have launched our 25 by 25 strategy, which is a strategy that aims, among other things, to increase the percentage of women we hire at CERN. We want to get to the 25% of women at CERN by 2025. Of course, this is an aspirational target, but it really shows a serious and clear commitment that we are having towards this. And last thing that I want to say is that it's very interesting how then the academia world is also now into this topic. It's exploring the topic and is growing into the topic, because we really believe that none of us should be an island. I'm representing CERN, and my fellow panelists, they're representing their own institution, but mainly we are representing ourselves as women working in science. And I'm the less scientist here in the panel. But definitely, it's a collaboration among all the institutions, among all the companies that work around STEM, moving together in the same direction. Thank you.
That was great to hear. Also from slightly, I love the CERN is academic, non-academic perspective. So I've passed then on to an even less, I suppose, inside academia perspective in a way, to Fanny Eugène. So please continue.
Yeah, that's what I was thinking. So I work for the Fonds de Recherche du Québec, which is the primary funding agencies in Quebec province in Canada. And what's particular about us is that we fund research in all fields. So STEM, of course, but also health-related research and social sciences, humanities, arts, and literature. So, of course, there are different challenges for women in those different sectors. So the Quebec Fund for STEM started pretty early, putting on measures for attracting more women to STEM. So we have several policies that have been put in place, but that have also been offered in the other two funds to make sure that we have the same consideration for all our students or researchers. So some of the policies, of course, are related to parental leave. So anyone who applies to our program, if there's a period of eligibility, the eligibility period can be extended if the person went on to maternity leave during this period. And the same is true for scholarship or grant holders who are allowed to postpone the grant payments or scholarship payments during parental leave. But for our scholarship holders, we also have a paid parental leave. So for 8 months, if they're allowed to take longer for parental leave, but for 8 months during parental leave, they get to receive the same funding that they would for their scholarship, and the scholarship is extended at the end. So, and this is offered to both women and men. We also want to encourage paternal leaves in our community. We also put in place implicit bias training for our reviewers. I can't remember, maybe 5 years ago, so 2018, I think. So that's something that is being done also at the federal level in Canada to make sure that reviewers are aware of the kinds of biases that can slip in during a review, not only gender related, but also related to the prestige of the institution, to racial considerations, age as well. And we also have this training for our personnel or staff as well. And another important thing that we consider is how the research is performed. So not only who does the research, but is the research considering sex and gender, which is also extremely important. So all applicants who propose a research project have to think about whether it's relevant to consider sex or gender, and explain if they do, how they're going to consider it, and if they don't, why they're not considering it. So this is not limit, like all our actions, the actions I've described relate to gender equality, but since 2021, we also have a larger strategy on EDI, so equity, diversity, inclusion. So we've moved beyond gender equality to include other aspects of diversity and other aspects of gender as well. We've had data on women and men, but now we have data on beyond the binary, so in gender diverse individuals. And so our actions always have this intersectional lens to make sure that we're not we don't have a specific group in our blind spot.
Lovely also to hear about, as you said, those intersectional actions. That I think is a really, really important topic. And lastly, we come on to Marie-Françoise to see if you would like to add some detail for us. Marie-Françoise, you're muted.
Okay. Yes. Well, so I must say I really like all the presentations, because they are insisting on various aspects of how to reduce the gender gap. So Yvonne insisted on the importance of these role models and education, and then there was also these examples from what is done in CERN and in Quebec. And I think that's what we need. I think we need to really exchange these good practices, and it's something we want to do in a more systematic way after the Gender Gap in Science project and inside this Standing Committee for Gender Equality in Science, to have really a forum of discussion on what people do and what is working better, and what is improving the situation. So, for example, one thing we found very useful in mathematics, because I was the chair of this committee for women in mathematics, as was mentioned, is to have an international network of kind of, we call them CWM ambassadors. So CWM was the Committee for Women in Mathematics, And we've been inviting people to be representatives in their own country in order to collect the data and also to create their own network and to distribute information. And we think this is also giving really a very good ground for making changes to have these exchanges between people in various contexts, in various countries, in various continents, and being able to have them really do a network and work together. So I think that's one aspect which I consider as very important, and I would like really to encourage also people to work this way in other disciplines. But okay, so I think that's what I wanted to say. Maybe I would add one thing we really discovered when we were studying this, when we were looking at this gender gap in science project, the results from the global survey is that when you look at the gender gap, maybe sometimes you discover some other problems. Like, for example, when we were comparing Africa and the rest of the world, we noticed that sometimes the difference between men and women in Africa is less important than the difference between Africa and the rest of the world in terms of being, say, having problems with access to funding or access to resources and so on. So sometimes when you look at the gender gap, you also discover some more other social problems. And I also believe that in terms of diversity, I mean, I noticed, for example, at the International Mathematical Union, we have this Committee for Women in Mathematics, but there is also now a new committee called Committee on Diversity. And we see that the techniques we are using to do this network of women can be very useful also for having other networks, for other communities, and for other forms of discrimination. So I think it's really very useful to have all these various approaches. That's what I wanted to say. Thank you.
So to kind of pick up then and carry on a little bit, I know we've talked a lot about policies, and it's actually really interesting to hear which different policies arise. I've really learned a lot. And I wanted to ask what you believe are the advantages of having more gender equality in the scientific community and in scientific research. So I'll start with Yvonne again, if that's okay.
Okay, thank you. I think that effort was done, but something is missing to reach the gap of parity between women and men. What I will suggest is that we have to go to the secondary level to do something, and I think that the panel I said we can, in each scientific event, we can organize in parallel with the participant, female participant, we can organize panel to show these ladies to people. And I think that girls are deemed to have no ambition, curiosity, and no capacity for long-term studies. This is due to communication. Because during years, I observed different contexts with women, either students or farmers. I noticed that the apparent lack of ambition is due to the lack of communication. So we have to strengthen the capacity of students, of scholars in communication. If they are good communicators, they can have a voice, they can be curious because they will ask questions. And if they ask questions, they help them to go more and more in high-level studies. So this kind of be improved in our institution. And because Amartya Sen, Nobel Prize in Economy, said, when women are educated, they gain a voice and they take a place in the society, which gives them more economic opportunity. So we have health in the world. You have also, women are not always eternal beneficiary. They have to participate also to produce knowledge, to make conception in problems, and so to have the solution for themselves. Not only men to build knowledge for women who are always beneficiary. So it's better to help this survival student who are in the university with good capacity in communication, and I think that they will have build their lives themselves. Thank you.
I will then ask Melania the same question of what you think gender equality can bring to the community as a whole, the scientific community as well.
Thank you. I think that maybe I would propose everybody to do one step back and not look only at the scientific community, but look at it from an organizational perspective. Burke and Dillon in 2018, they issued a report called The Diversity and Inclusion Revolution. It's a study, so it's a paper, it's science-based, although it's not physics, but I think it's social science. And they have analyzed the context in which they were working, and the outcome was very impressive, in my opinion. Like, organizations with an inclusive culture are 3 times as likely to be high-performing, 6 times more likely to be innovative and agile, and 8 times more likely to achieve a better business outcome. Now, let's take this and let's bring it into the scientific community. And I just have a question for all of us here. In the community, in the scientific community, where the general aim is to advance humanity, isn't all of this even more relevant? And I will conclude here. Thank you.
Think about there, I think it's always useful to, as you say, is take a step back. But I'll pass that on to Fanny Eugène.
Yes, I fully agree with what my colleagues said previously, and I'm gonna hit the nail on the head a little bit about what is being researched, because there are limitations to research on women's issues. We've known for a long time that a lot of studies, especially in health, have been done on men, and assuming that they were the standard, and without considering sex or gender. There are kind of famous stories of medications that had to be taken out off market because there were secondary effects on women because they hadn't been tested on women. And a study by Vincent Larivière showed that women are more likely to to take into consideration sex and gender in their research. And an even more recent study showed that showed the effect of gender and racial equalities in the scientific workforce on the advancement of science. And it shows that there are topics that are not covered that should be because of the lack of diversity in the scientific workforce. So there is a relationship between diversity in the workforce and expansion of the knowledge base. So a lot of topics would receive more attention if there was more gender equality in the scientific workforce, but not only gender, but also general equality in this. So it does affect what is being paid attention to in research. So what we know about the world.
I think you're so right. Yeah, I think the health is a really good example of where we have real inequality because of a lack of women. But I think another that is pertinent that I will bring up is artificial intelligence and diversity in the development of AI, which is, I think, a really interesting field. But I won't talk over anymore. And I will instead pass on to Marie-Françoise, who I think probably has something more interesting to say.
Yeah, so I think one other scientific topic which I find very interesting is archaeology, for which there were a lot of bias in consideration of archaeological research. And when someone was found with a sword, it was initially thought it's necessarily a man, but now with all the DNA analysis, we can find that sometimes in fact they were women warriors. So just to say, I think this is very important for scientists to be aware that, of course, it's maybe not so much the case inside mathematics, where we don't see directly a bias related to gender, but in many sciences, several were mentioned, like health, artificial intelligence, and archaeology. It plays really a very important role, and in many of them also. So I just wanted to encourage everybody to do what was done during this special day of the International Year, which is to involve inside the scientific activities as a side activity and something which is important to include, in fact, the discussions on gender and diversity inside the scientific events. And I think also what Yvonne was suggesting, that it's also scientists should also reach the younger people, secondary school people, and try to really tell them what science is about. So I think all these aspects are very important in order to promote gender equality. But I think also we should not get discouraged, because if you look, for example, at the proportion, we've been looking in our project to the percentage of women authoring mathematical papers in the last 50 years, and we discovered that the number is really growing. I mean, it was like from 10% to 27%. So things are changing. I think they are changing very slowly. I think that there is from time to time an evaluation on, given the rate of progress, how long it will take us to reach gender equality. And I think the current estimation is about 150 years based on the recent projects progress. So it's not going to happen immediately. It will take time. It will take really a lot of changes in everybody's mind, because women are not always supportive of women. Also, it's also something that needs to be said, and it's kind of also dialectic between what's going on in society in general and what is going on in science. But since education is so important, I think that the topic of gender equality in science has really a very big influence on society. So maybe I'll take one example, which is the case of Mariam Mirzakhani. So she was a mathematician from Iran, and then she went to study to the US, and she was the first woman to receive the Fields Medal. And her influence and impact in her own country is, I believe, really very important in the history of women in Iran. And we see that this history, unfortunately, is not yet the problems are not yet solved, but Iran, for example, is a country where there are many, many women in science. And I think it's this high proportion of women in science is really something meaningful also for all women more globally. So we are not just a little part of the population, we are really, I would say, a sector where gender equality is particularly relevant.
You're so right. I think a really fascinating example as well. I have a slightly different tack. So now we've established some policies that exist, and also why we generally believe that gender equality is really vital. I'm going to go a slightly different route and ask you each what you personally see are the main areas of challenge and concern surrounding gender equality or achieving gender equality in the region or the country where you live. So what do you see are the main barriers And I'll start again. We're going alphabetically. I'll start with Yvonne again.
Yes, me, I say that I think the main barrier is the communication. Ladies in Africa don't speak a lot. So I think that this is a barrier. But with the model, the women model, I think the student can see that a woman can be high level in education, be a scientist, a senior scientist with success stories, and that it's possible to do profession and to have a family and to see some happy ladies, scientists, happy ladies. I think this is very important, and I say that the local women are the most efficient. So I think the financial issue is a big point. To give scholarship to students, to give grant for doctoral studies, and also to plan some gender approach in the selection of some places at the university when there is some new application to be teacher. I think women can have there also some facilities. And so on, I think that the scientist women like me, it is an obligation to do something all your life, to show to younger students, to show to people that they can arrive if they want. So it is an obligation, and maybe some research can be done to see if what is the impact of all the activities we are planning for the benefits of students. Maybe it must be evaluated also. Thank you.
Thank you very much. I was just thinking how much I also would love to see more representation of happy women in science, not struggling, thriving, just happy.
Yes.
Melania, then I'll pass on to you next.
Of course, thank you very much. If I have to pick one of the many challenges that I think we all see in gender equality in science out there, I would probably drill it down to the difference between equality and equity. When it comes to gender equality, even in informal conversation, I often get this answer from, let's say, for a stereotypical male out there. Yeah, but who is telling women not to come? Who is telling women not to join? Who is telling women not to have a career in science? They can come the same way I came. They can come, and for them, this is what we should be offering. And now I'm speaking about like the very resistant people to change that likely are very few out there. I hope, I want to believe. And the answer is this: is like, yes, we want to have gender equality, but in order to have gender equality, we need to apply some equity, because the process that a very masculine-oriented society has put in place do not work for the women that are now entering, in the past century, are entering more the job market, historically speaking, with the difference between the different areas. This said, it's probably a cultural resistance, and the cultural trumps strategy for breakfast, as they always say, which means that is the most difficult thing to change is the culture of people. It's not about like, yeah, women want to come, let them come. It's like, no, let's make a moment of self-analysis. Let's kill our biases out there, starting from the recruitment, as Yvonne was mentioning before, and going on with all that is their work life and making it accessible for women. But a workplace that works for women works better for everybody else. So I think that this is really the biggest challenge out there, and this is to convince society, the most resistant part of society, that in order to achieve equality, gender equality in science and in other fields, we need to apply some equitable principles. Thank you.
So I think it's a really important point for people to listen to the kind of difference between equality and equity, because I think both are so important. So Fanny Eugène.
Yes, I'm fully behind what Melania just said about difference between equality and equity, and the fact that sometimes you need to, I don't know, shine a big light on the obstacles that some people have to go through, which may not be apparent to those who do not face those obstacles. And the academic culture, and I think that's everywhere, is a very particular culture that doesn't really make place for maternity leave or just parental responsibilities. So I think that's changing, but it's probably the biggest issue. And in Quebec, we have a fairly equal society, but of course we're not shielded from gender norms, so that the impact of stereotypes on little girls who don't see themselves as future scientists or as what we would call a genius, since like starting at age 5, that's also a problem. And I think that's everywhere because we're exposed to the same societal norms. But I think there's a lot of work on that. And you were talking, Melania, about resistance. And I think that if you've been following the news a little bit in our neighbor to the south, there is some resistance, pretty intense resistance to equality, to feminism, to anti-racism that's brewing. And I don't think we're immune to that. I mean, we've seen some signs of this coming. So I think that's going to be a very important thing to keep in mind in our communication, this resistance that's being a little bit more vocal these days.
Absolutely. I think actually sometimes that kind of more vocal resistance helps to defeat what Marie-Françoise was talking about earlier, like, you know, that fatigue or burnout that I think all sometimes probably experience. But speaking of, I'll pass on then to Marie-Françoise to wrap up the kind of formal part of the panel discussion.
Yeah. So I think one thing which was mentioned, which is really quite important, is the fact that we need really some specific initiatives towards women. So I think what was mentioned was, for example, of course, men or men, if they take care of children, like this extension of parental leave, for example, which was mentioned. But I think it's also some kind of much more global. I mean, like if there was some interruption in the work because of some workload related to having a child, but maybe taking care of someone in the family, I mean, some health issue and so on, we should not be, I think the kind of model for scientists is, as was mentioned already, someone with no interruption, with no flow, who's just totally devoted to science. And this does not work for many people. It doesn't work for women in many cases, but it also doesn't work for other people, other men even. So I think that to be more diverse, to accept more broken career paths, to accept people who are maybe more original, more different in their way of studying and doing research is really something also which plays a key role in being able to reduce the gender gap. But so in a way, we need some kind of universal principle that make it possible for everybody to be part of science. But we also need to be very aware of something that look like small details, but are not small details, which make it possible for people to to proceed in their career, even though they don't fall entirely in the kind of scheme of what is considered as being a scientist. So it's really something several of us said already. I mean, the importance of culture, the importance of model, what kind of person we want to advertise and to illustrate, and also we don't need only very big names as examples of scientists. We need many people, and if we are in Burkina Faso, of course, it's important to have women from the country which are taken as examples, and so I think all of these efforts is going to be important, to take time, but at the end to produce consequences. So that's what I wanted to say at that point.
Thank you so much, Marie-Françoise. Yeah, also I think a really excellent point about feeling represented within your own country as well. Something that we often don't think about. So we have a few more minutes, and I'd like to open up to some quick questions from our audience. If not, I have one question that I can go around and ask. Are there any questions? I will type any in the chat if they come up on YouTube. Oh, okay. I don't see any in the chat, but I've also just received a message saying that we have to wrap up. So we might have to wrap up actually. But I'd like to thank our panelists very much for what I think was a really fascinating discussion, and also for all their time in preparing this event and helping me out. So thank you very much.
Thank you
for organizing.
Thank you very much.
Bye.
Thank you very much. Goodbye.
Okay. Bye-bye.
Bye.
I want to thank you all for this interesting discussion. I hope we had more time to go on with this, but maybe in another occasion we will pick it up, these ideas and others. Thank you. And now I want to move on to introduce you Dr. Jihan Kamel. So she obtained her PhD from the University of Rome La Sapienza and held a researcher position at ENFN in Italy. Since 2015, she is the infrared beamline principal scientist at Sesame on leave from the physics department of Helwan University in Cairo, where she is a lecturer in biophysics. Up to date, she is the only female scientist at Sesame. She is also involved in the preparatory phases for the establishment of the African Light Source. She also organizes workshops and schools at the national and international levels to build awareness and highlight special topics linking science to industry and society. She is particularly noted for her lectures on science for peace and science diplomacy, as well as women in science. In 2020, she was indicated 2020 laureate of Eureka Prize of the French organization Amnesty. In 2021, she was selected as one of the 25 African women scientists within the African and Global Research and Development Communities Initiative. In 2023, she was one of the 6 women chosen by Nature to comment on their plans for International Women's Day. So it's a pleasure having you with us today. Please go on.
Thank you so much, Christina. I hope that my voice is okay now. Perfect. So I just start by sharing my screen. I hope it's okay.
All good.
Thank you. So thank you, Christina, for the invitation to join this inspiring event, as well as for the introduction. And I believe that we need more of such inspiring and also useful events to get experience exposed also from one side of the world to another. Actually, I try now in this presentation to answer or to give some insights as answers to the question that I chose as a title for this presentation, that is, have accelerators ever done for us? Of course, for time's sake, I'll not go into details of the Sustainable Development Goals However, I hope that also by the end of these 20 minutes to share some insights and that you can get some clues on how we are trying and doing our best also to implement many of these goals. The kind of particle accelerator that I'm highlighting in this presentation are the synchrotron light sources. And actually, synchrotron radiation was observed as Crab Nebula 6,000 light years ago, and also was observed in the labs in 1947. This kind of radiation is emitted through the acceleration of particles moving in a curved path with a speed close to the speed of light. And this opens actually a huge range of opportunities and complementarities if we want to couple more than technique to another. This radiation has unique properties that allow us to investigate virtually all sorts of matter for almost all applications. This kind of radiation, as we extract it or we work on it, produce it in a particle accelerator, is covering a wide range of electromagnetic radiation that takes into account the X-rays, whether hard X-rays, soft X-rays, ultraviolet, visible light, as well as infrared radiation. Is considered one of the most influential tools if we are focusing on different fields of scientific research. And this also can be considered as a giant microscope that give us a lot of information, a lot of answers about the microscopic world, about the invisible part of our world. We're not discussing more about the basic or applied, but of course, nothing can go on without focusing on fundamental and basic sciences such as physics, chemistry, biology. Of course, this can be still extended to different fields in between, such as biophysics, life science, material science, whatsoever. And this also, as I said, is extended to so many applications such as energy, pharmaceuticals, medicine. Many of the public health research is also produced and getting benefit out of these kind of accelerators, as well as for agriculture, for environment, energies, batteries, whatever you can think of. I believe that there is a space in our world of particle accelerators to give an answer to. Not only giving answers about our present or about our future, but also we can go back to our past, and also in this kind of accelerators, you can get some information about our history or about our ancient ancestors, like what you can see in this slide. We're doing a lot of experiments on cultural heritage, archaeology, bioarchaeology, and paleontology as well. Of course, all these kind of particle accelerators, as well as other infrastructures, have science, which is a common language, a neutral language that everybody understands. And this also moves towards common goals and taking into account and considers common values. And hopefully this also takes us to common impact on our societies. And again, it's very needed, as we just heard along this session, that we need to keep building up on the successful contributions in science, regardless of the cultures, regardless of any national labels, and also we need to learn from any failing experience. We need to learn from our mistakes and try to correct them along the way. And nothing is nicer than this image that I got, that we do not ask about any label for any of our scientists. We don't care about their religion, their nationality. We don't care about their political point of views. We care only about what we can achieve together as scientists. And again, sustainability, development, education, history, and young people are quite together in one loop. As I said, we are having these common purposes and common values together. And as we share 99.9% with each other as humans, that means we share also the same disease, pollution, energy, global warming, and COVID is not that far to teach us a lesson of how science and collaborations can help fighting such a pandemic that attacked all the globe, not only a particular region of the world. Of course, this also gets its impact on our economy, food security, and also disaster management. This goes typically beyond the individual capacity or budget of many countries. And I also impose this question, what if what we need is also more than money? This is a region that I take you closer, which is the Middle East region where we are now. And many opinions are tackling the international rights and social justice in this region. As you see that this region is always tinted with wars and political conflicts, whether for religious aspects or for political aspects as well. So the key that was used to go through these conflicts was to use science as a neutral tool to bring these people together. And this is why we say that Sesame was built as a model of science diplomacy in the region. Sesame is the first third-generation light source in the Middle East and neighboring region. It stands for synchrotron light for experimental science and applications in the Middle East, and is considered a symbol of cooperation, solidarity, and peace. If you just give it a quick look, Sesame started back in 1995 as a meeting to try to bring the people of the region together, the politicians, diplomats, and science diplomats. And that took almost 20 years to bring it eventually on Earth as a functional and operational particle accelerator of the region. We started as a donated machine and some equipment for beam lines and instrumentation as BC-1 that was dismantled from Germany. And what you see in this picture is Sesame in 2002 as these components left the harbor in Germany, going to its homeland finally in Jordan. This picture I see to the right is Sesame existing now in 2023. Of course, we are still using parts of this donated equipment, but Sesame went to an extensive upgrade, and we are running a totally new storage ring, which is the third accelerator of the facility. Sesame is an intergovernmental organization, and it's at the service of its members and also the whole world, because we are serving science. And it was modeled on CERN and was established under the umbrella of the UNESCO. Sesame members are currently those 8 you see now on this map. Those are without alphabetical order: Pakistan, Iran, Turkey, Jordan, Palestine, Cyprus, Egypt, and Israel. And it's not that difficult to understand why Sesame is a brilliant and unique example of science diplomacy in the region, bringing all these people together on one table in one facility to work only for science, leaving all their political conflicts aside. And again, we always ask this question, could that our past and also our present shape a new future for the region or not? This is something we are in the process of, but from the first insights, we believe that is going to work. Sesame also has extensive international support and it has its observers. Those are listed here in this slide. Almost all the European facilities, also other organizations such as CERN, UNESCO, the European Union, and so on. So to answer quickly in some bullets, what have accelerators ever done for us? So we can say that they help establishing world-class basic and applied research, interdisciplinary, of course, and multidisciplinary. These can also provide a healthy environment for collaborations and individual development, training graduate students. Those no longer need to go abroad looking for opportunities. Another crucial point for our region is that we're trying to attract scientists working abroad to return with this, trying to reverse the brain drain and also the internal brain drain. And I think this is also something that is that can be, I would say, extended to other facilities all over the world, not only in our region. One major importance of such facilities also is to address local or regional concerns, whether biomedical, environmental, whatever, and also to promote capacity building with different aspects such as scientific, economic, or also human capacity building. With that, it also develop economy and high-tech industry. And as we just heard, we are also targeting to decrease the gender gap as much as possible. Of course, because there are many barriers and obstacles that we are trying to overcome in this region. In other words, this is one of my favorite phrases about particle accelerators, that they are operating in a democratic mode. And that means we are using scientific cooperation to promote peace and understanding between people from different traditions, religions, and also political systems. To take you closer, when I said, what if what we need is more than money, of course, we have a lot of financial challenges and shortage to get the facility going on. But what if you need more than that? What if you need peace? We believe that Sesame is just in the right place to bring us forward to a peaceful state of existence and cooperation. And this, of course, will have its impact on all the societies in the region. Another thing that was also noted, and many efforts are going in this direction also, is to, as I said, decrease the gender gap, taking also the women rights to compete for a scientific career as a human right that needs all the respect, all support, and encouraging. The other third major point for us, again, is the brain drain reversal. And what you see in this map, it confirms how the low and middle income countries, mostly existing in our region, are severely affected by the brain drain, where all the large-scale immigration with technical skills and knowledge escape from the region to a better opportunity. This is a map that I believe how it's seen by politicians, policymakers, and diplomats, and this is the one I believe we scientists are targeting, and we are trying to implement it also in our in our life as not only as scientists, but also as human beings. And this is two maps that considers different kind of collaborations between scientists from different nationalities and backgrounds. But again, we need to understand that science diplomacy works better with the challenging relationships, but also it does not work without a real scientific exchange. This is an image to show you what we call science diplomacy in Sesame, that different countries are all collaborating regardless of any conflict to build just one cell of the accelerator. In 2017, Sesame was finally officially inaugurated. And in 2018, we became the first associate of the League of European Accelerator-based photon sources. And in 2019, Sesame became the first and, to our knowledge, the only particle accelerator complex that is fully powered by renewable energy with a generous support from the European Union. Sesame storage ring is 2.5 giga-electron volt, and we are aiming for 400 milliamps. So far, we are working with 300 milliamp. And we have the capacity to 24 beam lines serving different techniques for different applications. But we are starting with what we call it phase 1 beam lines. Those are these 8 phase 1 beam lines. We have so far 3 operational beam lines and 2 are coming soon in this, actually by the end of this year, we'll have 5 operational beam lines. The progress of our success is measured actually by the number of the proposals those we received for the 3 operational beam lines so far. It's tremendous success for our region. And we believe that with the addition of the next 2 beam lines by the end of this year, we will also have a stronger position as synchrotron facility. A 6th branch for the 5th beam line is also another sign of success because it's funded by one of the Sesame members for the first time. So we're building a strong community, not only for us as staff, but we are also targeting the scientific community of the Middle East and from all over the world. And what you see in this pie chart is just some examples of our users. Those come to perform their scientific research at Sesame. They are not only from Sesame members, but they are also from other countries as well, like from United Arab Emirates, Qatar, Oman, Netherlands, Morocco, Malta, Malaysia. Those are not Sesame members. And this also takes us to another level of transferring the know-how and the experience that we got through also training, through collaborations, through training opportunities and networking, that also proves to establish a tangible implementation of the Sustainable Development Goals. So the next mile for us and for the particle accelerator community also is to establish an African light source. And it's quite known that there's over 60 synchrotron light sources all over the world, but none in Africa. And we are all hand by hand working extensively towards fulfilling the dream of Africa by funding and founding the first African light source. The reasons are still the same. The particle accelerator in Africa will still do the same job as for any other particle accelerator, and just mentioning a few examples on public health in Africa, such as malaria, HIV, different kind of cancers, maternal mortality. But not only that, there's also the very rich cultural heritage disciplines in Africa and also beyond, such as water pollution, agriculture, and environment. To end with this, I would just mention that what you see here, all these organizations, all these facilities, and not only particle accelerators, also other infrastructures and institutions are showing a huge support for establishing the first particle accelerator in Africa. And Sesame was the first particle accelerator also to sign an MOU with the FLS Foundation in 2021. I end with one of my favorite quotes also for Nelson Mandela. That is, after climbing a great hill, one only finds that there are many more hills to climb. And Sesame was one of them. And we hope that the African lessors will be the next hill to climb. Thank you so much.
Thank you, Jihan. Amazing presentation. Let me ask you a question, picking up on the science diplomacy. Who are or who should be the main drivers in science diplomacy? Are we talking about scientists or who in particular should be?
Well, actually, usually when we mention this, we go mentioning both scientists and the politicians and diplomats. So it's like going both ways, and because experience showed us that one way is not enough.
So they should work hand in hand.
Yes, should be always hand in hand, yes.
Okay, thank you.
Thank you.
Then we have our last speaker, Leivan Koblenz. His career crisscrosses multiple sectors of science, technology, education, and sustainable development. At the US Nuclear Regulatory Commission, he applied mathematical models of probabilistic risk to improve safety practices at nuclear power plants. In the US Congress, he led Senator Lou Lieberman's effort to create the E-Government Act of 2002. At the International Atomic Energy Agency from 2000 to 2008, he worked with Director General Mohammed El-Baradei on nuclear diplomacy in Iraq, Iran, and other political hotspots, while also promoting high-tech improvements to agricultural productivity, medicine, and groundwater management in developing countries. From the International Atomic Energy Agency, he returned to New York to create new university and community-based models for entrepreneurship, drawing on the maker movement and the democratization of advanced manufacturing. For the last 8 years, he has been the head of communication at ITER in the south of France, where 35 countries are collaborating to make fusion power a practical reality for clean energy generation. He is also the chairman of Cloque, a US-based cybersecurity startup venture. Thank you for joining us, Leivan. Please go ahead with your presentation.
Thank you very much for having me, Christina, and congratulations to Dr. Kamel on what was a superb presentation on actually one of our relative distant partners. We do work a bit with Sesame, so it's good to see this, and particularly the international collaboration that was that you emphasized so well in your presentation.
Thank you.
I will try to share my screen here and hope I have the same good luck that that Dr. Kamel had. You can all see my screen? Yeah, okay, good. So I'll try also to get into there we go. I would also say, just for the record, that if you hear thunder and lightning in the background, the weather here in the south of Provence, in the south of France, in Provence, is normally beautiful, but you're catching me right in the middle of a thunderstorm. So what I will be trying to illustrate with my presentation is a way in which basic and applied science are kind of converging here at ITER. If you look at our work site, this is the overview from a drone. It's about 1 kilometer long and about 400 meters wide. We are trying to build the first industrial scale fusion power device. And if you look at all the nuclear devices that generate energy today, they're all fission. Fusion is different. I'll explain the physics a little bit and then go on to show sort of how that actually works. But I also will try to illustrate the degree to which international collaboration is a part. There's never been a project like this. So why do I say that? This switchyard, for example, was largely built with parts manufactured and shipped from the US. It's a steady state shipyard. Here you have parts in a pulse power shipyard that are largely from China. Here, where our magnet conversion buildings are, you have parts from India, China, Russia, and Republic of Korea. This is mostly a cryogenics plant built in part from components made by France, some by India. And that is simply a microcosm of how this plant is put together. The components are made on 3 continents and shipped like a giant Lego that is supposed to somehow fit with the desired precision. This building, for example, the gray building at center left, is the only building owned by India, because India is building this gigantic vessel, this cryostat that houses everything in a light vacuum in a cool environment. And because it's 30 meters high and 30 meters wide, it could not possibly be shipped. So from these magnificent forging facilities in Hazira, India shipped precision parts, about 56 parts here, and then an Indian team supervising a group of German welders under French nuclear regulation and using a form of stainless steel developed elsewhere in Europe, put this piece together that would house everything to make this fusion device. So that sounds like a lot like applied science, and it is, but it is also basic science, and I'll try to illustrate a bit what I mean by that. So when you see these flags that fly on our work site, you know, seeing China flying next to Europe or seeing Russia flying next to the US, where else would you see that? Maybe at the United Nations or maybe at the FIFA World Cup. But for all of these countries to actually be contributing parts, when in the news, what you will normally see is trade wars or disagreements or even armed conflict in this or that region, this is really a 40-year commitment because of a common goal. And what Dr. Cabell was talking about, and actually, Christina, what you asked about with science diplomacy, this is actually very much a common goal that we can transform our energy legacy, not only for, say, the Sustainable Development Goal 7 on clean energy, but also addressing climate change, addressing inequality, etc. So the science. Fusion in the universe, this is the reason that we all exist. Fusion is the reason for light and heat and life itself on Earth. At the center of our sun, we think of it as a large ball of hydrogen, which it is, and gas, which it is, but with the sun being 300,000 times the density of Earth, at the center of the sun, you really have hydrogen at about 70 times the density of steel. So proton-proton fusion occurs by crush, gravitational crush. The particles are forced together. To try to reproduce that, we've kind of figured that out, that this was fusion about 100 years ago, roughly 1920. But figuring out how we could possibly harness this on Earth seemed impossible because we cannot reproduce this gravitational force. So there are several ways that are brought about that we try to make this happen, fusion on Earth. The one that we're trying to do here is probably the most advanced, arguably. Some would dispute that. It's certainly among the most commonly tried. We call it magnetic confinement fusion. So in this device, which is called a tokamak, which is a toroidal shape or a donut shape, you have a magnetic field. So it's toroidal shaped magnetic field and a Russian acronym that came up with tokamak. What that means is that this metal cage has an invisible magnetic cage that conforms almost precisely to this shape. And within that, we put a tiny bit of gas, 2 forms of hydrogen, deuterium with an extra neutron and tritium with 2 extra neutrons. And we we inject heating systems until we get this to 150 million degrees, 10 times hotter approximately than the core of the sun, which is the speed at which these particles, when there's an electric current here that has ionized them, so you've got all charged particles or mostly charged particles, these gaseous nuclei will overcome their positive attraction and hit and fuse and join together. And in that, a tiny bit of the mass will be given off as energy so that the charge, the mega electron volts of the particles that leave, you see the helium nucleus here is 5 times larger, 5 times more energetic than the incoming particles, which will allow the helium nucleus to continue to heat the plasma until we get to a point of a burning or largely self-heating plasma. The neutron is the exception. It's of course not a charged particle, so it will escape the magnetic field, transfer its kinetic energy to the wall of the tokamak, to the steel, and heat the water that circulates behind it. In a commercial plant, this would be expected to produce electricity, although ITER will not produce electricity. We are trying to observe a phenomenon that's never been preserved on Earth. This is the basic science. The only time, I mean, we can't observe the center of the sun too directly, obviously. And on Earth, the only time we've had a burning plasma is really in an H-bomb, right? So to be able to observe a controlled burning plasma for pulses of about 6.5 minutes, that's the ITER design, that would be unprecedented. So there is plasma physics basic phenomena, and there is where the basic science will be coming at ITER. Now, why? Yes, it's for applied reasons, because if we can harness this, we have baseload power, carbon-free, with an abundant supply of deuterium, and then tritium, which is very scarce in nature, we would breed by placing lithium in the walls of the reactor so that the tritium, the neutron hitting the wall could also be breeding more tritium fuel. So that's why we say abundant fuel supply. And as long as we choose the right materials for the walls, there's no long-lived radioactive waste products, and it's extremely safe. You do not, unlike fission, where you have, say, a couple of 100 tons of uranium or plutonium as your fuel in the reactor, here you have 2 to 3 grams of hydrogen, no radioactive product in the helium, and what you have essentially is the neutron radiation, and then the walls, of course, will get activated. And if you choose your materials wisely, we should not have any long-lived high radioactive waste. In addition, it's not a chain reaction, so it's very difficult to do, but if it works and you have a problem, it shuts down instantly. There is no possibility in this physics of a Chernobyl or Fukushima, etc. So I've pretty much covered how it works. You inject the gas, you run a current to make it an ionized gas or a plasma, and then you use multiple heating systems. So the challenge is containing it. So the way that you contain it, you have a central magnet here, largely made in this case in San Diego. You have D-shaped magnets that go here around the outside. Those are mostly made half in Italy, half in Japan. You have circular magnets that are difficult to see here because this is a cutaway, but you can see this one at the top. This was made in St. Petersburg in Russia. It just arrived on our work site in the middle of February. The others were either too large to be made and shipped, so they were made here on the site, or the one at the very bottom was made in China and shipped here. It's already installed. So the idea was born in 1985 when Reagan and Gorbachev were trying to reduce their weapons arsenals, and they ended up with the plan to make something positive as well, to make ITER. Japan and Europe joined quite quickly, and the design discussions went on through the 90s. Then in the 2000s, China and Korea and India joined, and the agreement was signed in 2006. Now we get questions. We've had questions from Jordan, from United Arab Emirates, from others about the possibility of others joining. And the answer is this is open to anyone, to any country that can show that it's got the political will and some financial contribution and also the scientific capabilities. But the idea of 1985 was very explicitly written for the benefit of all humankind. So all the members wanted to be the host because they thought their companies would benefit from building this. And so the agreement was that Europe would contribute 45% and the other non-European members contribute 9%, but not as cash. Most of it, 80 to 90%, would be contributed as components. And that's where we got to this rather strange procurement of the components, the more than 1 million components that go into the tokamak itself, plus all of the different components that go around the outside. So as I said, here you see the human scale of the human at the bottom of this figure. You have a giant central solenoid made in 6 modules in the US, and then the various contributions from Japan and Italy, Europe for the D-shaped toroidal field coils, and the manufacture of the circular magnets in China and Russia and Europe. And if you go to the overall cryostat, really there are more than 1 million components in here. So this is an extraordinarily oversimplified breakdown. But the key is that all of the intellectual property coming out of this is shared with all members. So whether it goes on for more basic science or more applied science, it's really a shared device. So I'll give you just a few photographs and then talk about the global industry. The photographs just show you what it's like to assemble this machine, a 30-meter diameter first piece that gets lifted by these overhead cranes, taken and dropped into this pit, so that when it is put in the pit, there's the top-down view, and you can see there the welding lines of what I was describing earlier, the German engineers welding under Indian supervision and French nuclear safety regulation, but still getting to an extremely high tolerance. This was the second piece, which goes on top and gets welded around just to create the general case that everything would fit into. Here you have the Chinese-made magnet, the first magnet weighing about 400 tons. So you're talking more than a fully loaded 747 jetliner there. And that's true of most of these big magnets. The next one, a little larger in size, a little bit lighter in weight, made here on site. And then here what you have is a 40-degree segment of the 360-degree tokamak, the vacuum vessel. So you mount on this magnet, on this vacuum vessel sector, which was made in Korea, 2 Japanese-made D-shaped magnets, and then in between, I'll show you in a later photo, a thermal shield that goes in between. Almost all of this is first-of-a-kind components. Here you can see, after it's lowered into the pit, what this looks like. So here we were doing most of this through COVID, the assembly photos you've seen, making progress at a slower rate, understanding the challenges. And now we've recently come across some leaks that are in these thermal shields where the gaseous helium circulates to keep the barrier between the interior, 150 million degrees, and these superconductor magnets, which have to be cooled to almost absolute zero, minus 269 degrees Celsius or 4 degrees Kelvin. So right now, we're taking a step backward to work on some of the repairs, and we'll get back on track. Meanwhile, around the facility, we see the cooling water system, quite a normal cooling water system, just a very, very high degree of capacity, able to remove 1.2 gigawatts of heat. Now in its pre-commissioning, here are some other examples where you have Korean transformers, Chinese transformers, which have come from different parts of the world, and they actually look different one to the other, but they have exactly the same technical specifications. If you go around the world, you might have heard about fusion of a different kind, where lasers were shot at a tiny, tiny plasma pellet in the US. This is inertial confinement, also making progress. Here in Germany, you have what's called a stellarator, which is like a tokamak, but more twisted, much smaller than ITER, but also making progress. And recently, especially in the last 5 years, a lot of private sector people coming up with their own projects, some of them drawing off of ITER, and certainly all of us working together toward a common goal. And then if you look at what we've done with superconductors, it has created advances in being able to map the human brain, or in a more applied way, enhanced electric train bodies based on some of the work that we did on complex aluminum structures. our diagnostics, which are many of them unprecedented, are helping with geothermal energy, laser welding, cancer treatment, etc. And there's more, many more spin-offs. So I will stop there. That is my overall presentation. Here we have photoshopped ITER into the Milky Way because really ITER is more or less making a small sun on Earth. And so that brings my presentation to a close.
Thank you, Leiven. A very good presentation. I think you have not commented on that, but do you think is still fusion on time to help us with climate change?
Yes and no. I think if you look at how long it takes to roll out a new energy technology, the solar installations and wind installations that we're seeing now were really pioneered in the probably 1980s, when you were starting to see the very first, not full-scale solar plants. So rolling out a technology like fusion and having our goals of countries trying to get to net zero by 2050 or earlier, there is one way that you could look at it and say no. But I will be completely honest, I'm a bit of a cynic for two reasons. One is that for us to really be sustainably developing, we have to think about countries that are still very short on electricity, the lifestyles that they want to build. So we're actually going to see energy, probably, even though we're trying to make it more green, we're going to see more doubling, some project tripling of energy use by the end of the century. So the only way we're going to be able to do that is if we harness solar and wind and renewables for where they are most well suited, but also new technologies like fusion that will help us to be green for the longer term. So different scientists will give you different timelines for when they want to bring fusion on the grid. But even if we had a perfect fusion plant today, to scale that up to replace fossil fuels means we need to have large scale use of clean concrete or steel production, other kinds of technologies. And so to get the generations of plants that will really roll out, I think it will take longer by the time we have enough plants, longer than 2050. But I also personally do not believe we're going to avoid the 1.5 or 2 degrees of warming. I think we will have most likely some irreversible damage from climate change, which means actually with sea level rise and more impact, we will need more energy. So I think the answer is yes and no, depending on how you view that question.
I see. So I've seen also in your presentation that is a collaborative effort. So ITER is definitely a collaborative effort. And I see also in your answer that if we want to do actually something towards climate change, we also have to use all we have. So even fusion would not be sufficient. We should use all our tools. And I don't know if, just a comment, just before we had a section with interview with scientists, and I asked almost all of them what scientific breakthrough would they like to see in the coming years. So like to be a little bit creative. And we received a lot of answers in the direction of energy conversion, energy storage. All of these were more or less unitary in this direction. And just one last comment, because now we have a little bit, 1-2 minutes left. Just today at lunchtime, I heard of a startup on fusion. Would this private sector endanger the future of ITER? Or on the other way, we are talking about collaboration, would be something that we all could profit from?
Yeah, the answer again is ambivalent a little bit. Certainly they will not make ITER obsolete at all, because we're like a giant national lab. We're just a national lab for 35 countries all working together. And hopefully, you know, Kazakhstan has joined as an associate member, so has Australia. Canada is working on it. We've talked to Iran. That was part of the Iran nuclear deal, which is kind of now in suspense. But the truth is that this will be a lab, a global laboratory where people can really study. And the other private sector initiatives, quite rightly, are viewed toward commercial deployment. So they are not trying to invite, you know, all the scientists to come and study. They're making machines that in some cases will destroy themselves, but with a really good set of data coming out of that, that's planned. So the private sector, when I talk to them, say ITER inspired us. This is, if you look 15 years ago, there were maybe 1 or 2 private sector facilities. Now that ITER has shown this growth over the last 7 or 8 years, it's hard to keep up. Literally, we have something like 35 private sector initiatives with roughly $5 billion put in over the last, say, 2-3 years. So that is exploding. And that says that even some of them will fail, no question, but that says that we're getting closer to making this a reality.
Mm-hmm. And you see, I asked Jihan before about her impression on who should be driving science diplomacy. Can we also have your opinion on this?
To be honest, the science diplomacy has to come from 3 sectors. It has to come from universities, because and teachers, even at the grade school level, because this is what inspires the generations that are going to make a better future. So we need that inspiration. That is where science diplomacy starts, in kindergarten. It's a way to help us view each other as a globally connected family. And then it is the researchers, the ones at ITER and so forth, who, yes, are the scientists and so forth, that need to get out. And you will find in the origins of ITER, way back in the 50s, there was a soldier who he really wanted to be a physicist, but he got conscripted by the Soviet Union into World War II. And it was only after the war, when he had no education and just a stack of physics books, that he was stationed by himself, and he came up with this idea of a tokamak that led to ITER. And about 9 years later, the Soviet Union did one of the most absurd things in the history of civilization. They went to the UK to make a presentation of largely classified material, to just say, let's share what we have. And of course, the Americans and the British were totally suspicious and said, they must be fooling us. But the scientists on the margins of the global Atoms for Peace conferences were the ones who shared data and said, actually, yes, this has merit. And that's why fusion has been, I think, quite unique, where the scientists and the politicians and the teachers all need to advance science diplomacy.
So collaborative effort again. Yes. Very good. Thank you very much for your talk. So we are getting to an end. So we only have 5 minutes left. And at the very beginning of this 4 hours time slot, I was presenting the periodic table challenge. I'm not so sure if we have already some results. Yeah, Bianca, can you tell us something about that?
Hi, everyone. So again, on behalf of IOPAC, we just want to thank those that have participated in this year's challenge. So as a reminder, since its inception in 2019, we've had players from over 160 countries. And throughout the challenge so far, we've had players from over 40 countries answering over 100 questions correctly this far. So we'd like to encourage you to continue playing as the challenge draws to an end, and to also encourage your colleagues. And just a reminder, we'll be providing multiple updates on the challenge as the 24 hours progresses. And tomorrow we'll be announcing 3 randomly selected winners at 4:45.
I was muted, sorry. Thank you. So I also invite those of you who has not participated yet to do it. I also plan to participate in the challenge. And I think with this, it is time to finalize this time slot. I'm greatly pleased for all the contributions we had today. I've learned a lot. At the beginning of this session, I said I am a science enthusiast. I can tell you I am a little bit more now. I hope some other people also share this feeling. We have learned about collaboration. We have learned about how to do things together, how to use multidisciplinary teams. We have also heard wishes for the future. The interviews were very interesting as well, and very inspiring. Also, the gender panel, the panel on gender equality was really interesting. I also pick up some ideas. And yeah, I would like to thank, besides all the participants that were the most important ones, we also had a lot of technical support. And I also want to thank all of them, also from European XFEL. We got quite some help, and to all the organizers. I hope you all enjoyed this. And this can go on. So we have 2 time slots left, or 3 actually. So all of you can still continue savoring science via YouTube in the next hours. So thank you very much, and I hope you all enjoyed that. Bye-bye.
Thanks so much.
Thank you.
Thank you. Bye.